Welcome, everyone. Thank you for coming to the conceptual design review for the MASA-Dearborn rocketry team for the 2021-22 competition year. We've definitely got some cool projects and interesting things that we're doing this year, and we're looking forward to getting your feedback on them as we move forward. So the first thing that we have is, I guess, me. I'm the new president. My name's Justin Kissel. I'm the former electrical lead, and then I was elected to president just a couple months ago, right at the start of this project. Continuing on, this project is named H.A.S.M.A.T, the High Altitude Soil Microorganism Analyzing Test Rocket. We have a lot of fun with acronyms here. So a bit more cohesive than beam laser from last time, if I do say so myself. But so let's get started. Standard overview. These times are, somewhat set in stone, somewhat not. We're going to present through all of the admin and all of the airframe and propulsion sections, and then we're going to have, a bit of a 5-10 minute intermission, and then we will present the payload, recovery, and then the project management and business sections after. Team member breakdown, we currently have 31 members, 18 of which are men and 13 of which are women. A couple of the we have everyone's majors listed here. So we've got MEs, a lot of MEs, a lot of EEs, and then a few combination EEs and CEs for electrical and computer engineers, and combination mechanical and biological engineers, especially for our experiment last year and this year, which we'll go over in a bit. Something new this year, we have certified flyers to show. We have 5 certified flyers on the team. Sierra Stockwell, our former president, is level 2 certified. Kyle Johnson, our former power lead, is level 2 certified. I myself am level 1 certified and will be attempting for level 2 actually on Saturday. Alexander Burkhart is level 1 certified. He's our current recovery lead. And Joshua Hawkins, our electrical lead, is level 1 certified. If you'd like to see any of the videos of these certifications, they are all on our YouTube channel, MASA-Dearborn Rocketry. I'll be sure to mention the name again right at the end, but you can see there we upload all of our launches and any other testing that we do, as well as these sorts of presentations. The overall team structure, so like I said, my name is Justin Kissel, I'm the president. Starting from the left, we have Sarah Dormal, who is our mechanical lead. She's our former airframe and propulsion lead. Joshua Hawkins is our electrical lead. He was formerly our data lead last year. And Sierra Stockwell is our current business lead. This is an interim position. Sierra's our former president, but we're lacking in any business members currently, so Sierra stepped into that role. And we're so early in the project that we don't have a safety and launch operations person picked out yet, but I imagine that will happen sooner than later. Spaceport America Cup. This is the competition that we compete in every year. So our objective is to bring a payload to a target apogee. Let me just admit someone to the meeting here real quick. And we compete in the 10K COTS category, and our target altitude is 10,000 feet. I know that I said in a couple of our emails that we're going to be moving to 30,000 feet this year. However, as we'll discuss a bit later, that has changed back to 10,000 feet. However, that 30,000 foot component won't be lost, which I'll explain in just a couple slides. Being in the COTS category, our motors are bought through a vendor. We don't make them ourselves. And the dates have been released for Spaceport America Cup next year. That'll be June 21st through 25th. Hosted by ESRA and sponsored by Spaceport America. So this is what I was talking about for not necessarily going in the 30K COTS category, but building a rocket for 30K. So we originally designed this rocket to go to 30,000 feet, so with a 2-stage motor, so a complex rocket. However, there were several limitations with this going straight to 30K. Our timeline is very strenuous this year. We're going to have a lot of new members, and a lot of our members, we've got a lot of design experience, but not a lot of manufacturing experience, which is something that we definitely want going into 30K. So building the 10K will get us that experience. We originally counted on this test launch that we're going to do in September to give us this experience. However, that makes our timeline so tight that it wouldn't work very well for us. But this will give us more time to train new members for manufacturing, so we can have more newer people manufacturing the rocket and get more team involvement overall. So to reiterate, for competition, we're going to have one motor. We're going to launch to 10,000 feet. It'll be boosted dart configuration. And then as long as everything's successful with recovery, then we will use the same rocket. We'll just put a motor in the upper stage, and we'll have a 2-stage rocket that we can launch out in Kansas to 30K, which can be a test launch for next year. A couple things that we've got to do for 30K is we've got to do more research into air starts, which I was hoping to talk to a couple people about today. And we use mock immune altimeters, which is fairly easy for us as we're already using RRC series altimeters. We just have to use RRC3s for everything now. So this was our point breakdown for this last year. The rubric was a bit different than years prior because it was all online. So we had 100 points for the entry form and progress updates, which we received all of. 400 points for technical report, broken down into 3 sections you can see in the middle. We received 330.2. And 500 points for the actual meat of the conference. So we had a video we submitted, and then we had a 15-minute talk with the judges. This resulted in us getting 418.3 points. No bonus points were available this year, unless it was CubeSat, but that did not apply to us. So we got 848.5 points. For this next year's projection, I'm comparing this to the last time that we launched because I'm assuming that the SAC point breakdown, it'll be more similar to that than the online competition. So less points for entry updates. We expect to get full points on that. We expect to do better in our technical report than we did that year. Design implementation, we plan to stay similar. 240 is the maximum amount of points that you can get. Flight performance, I have a bit of a question mark next to. I've looked at a lot of scores for the Spaceport America Cup, and I cannot figure out what formula they're using to calculate the flight performance, because it's out of 500, and 150 is just pass-fail. But only 17 teams out of 120 got more than 330, which I found fairly odd. So if anyone in this call happens to know how that's calculated, if Robert had joined, or if Robert's here, please let me know. If you can tell me how this is calculated, I'd like to know. We plan to get no penalties, similar to the last time we launched, and we plan to get bonus points. We want to launch the first day, so 100 points there. Thank you, Trent. I will look for that equation in the ESRA documentation. And 50 points flat because we're doing CubeSat this year, which brings us to a total of 940 points, which seems high relating to the 754, but remember, this last year we got 848. So some of our goals this season, we want to launch a competition, and our plan is to launch the first day of competition to get those bonus points like we were talking about. We want to retain at least 20 new members. We've got a lot of members graduating, so we want to refill our membership and get some more people on the team, especially younger people. We want to place top 15 overall. We placed 22nd this last year, 10th in COTS, which we think is very good, 10K COTS that is. So we only plan to go up. And we plan to get 15 plus members L1 certified. We want to get our entire airframe and propulsion team L1 certified, and Sierra is going to be holding a class for new members, which I'll talk about in a bit about certifications. The vehicle architecture, so it's fairly similar with the boosted dart configuration. You'll see that there is a second motor in here, but this is just a tube. It's going to be empty for competition. So we'll start on the left and work our way right. So in the dart, we have a custom GPS and a tele-GPS. We have both. Our CubeSat payload, camera shrouds. In the CubeSat, there's the soil experiment, which I'll talk about in a bit. Dart parachute. The ARM, which is sort of our replacement for the flight package naming scheme, which Airframe will talk about in their slides. The air brakes is still a system. Deployable fins at the base of the dart. The booster main parachute. The drogue avionics. The booster recovery eBay. And the new member payload, which is another new thing we're doing this year. The bottom motor and airfoil fins, which is another big project that we're doing on Airframe. So a bit of a comparison between our rocket. You see we've got a lot similar. We're keeping our air brakes. We're keeping deployable fins. We're not going to create our own body tubes or nose cone this year. And we're going to keep our 10,000 foot apogee. Some different things that we're doing. We're changing experiments to a soil microorganism experiment. It's going to be designed for 2-stage, but it's only going to launch with a single stage for competition. We have a CubeSat payload as opposed to the Von Karman payload. 6-inch instead of 5-inch diameter. This is to accommodate that CubeSat. And this rocket will be capable of 30,000 feet by adding another motor in. And a primary GPS this year will be the custom GPS, which we'll talk about in the recovery section. Just a quick summary for our payload. We want to analyze soil health through microorganism activity. It's one of the big factors for keeping soil healthy is having a diverse and large quantity of microorganisms. So we want to determine if they stay alive through flight, and we want to monitor a few different things: humidity, temperature, CO2. pH is the real hard one to monitor because those sensors are so large. So we're just going to monitor it before and after flight and see if there was a big change. And everything else we're just going to monitor during the flight. And we're hoping that the soil will stay alive. And this has relevancy, you know, to taking soil either to other planets or to outer space. We want to make sure it stays as rich as it can be on Earth. Launch vehicle summary. It is 179 inches long, or just under 15 feet. The motor choice, we've got two different motors that we can use. For competition, we're going to be using the N1100P for the 10K launch. And then for the 30K launch after competition, we've got an O3400 in the base and an M2500, which we already have one, in the Dart. Our recovery system, we are going to be deciding between a drogue mortar and reefed parachute setup. Alex will speak more on this. He's going to do some testing with the reefed parachute. We want to test it on a smaller scale before we move to a large scale launch with it. This is our overall timeline. The events in bold on the left pertain to our current 10K rocket. This is Boosted Bear, the next generation. And the bolded events on the right is for Sierra's new member CERT rocket class. So we'll start on the left here and we'll work down. You'll see purchasing began for this current rocket, Boosted Bear, the next generation, early July. The manufacturing has been going on since July, and we plan to launch that rocket September 25th. It's a very aggressive schedule for this launch to happen, but I think that we can get close to our goal. We've already done some manufacturing and we plan to get more. One big holdup is purchasing from the university, but we'll get through it as we always have. Back to our standard timeline, we had payload competition, then soft concepts, then hard concepts, and then our conceptual design review. You'll notice this is the day before our design season starts. So if designs aren't fully fleshed out or anything, that's because our season hasn't started yet. So please allow us a bit of leeway there. And then after that, design will go on for a few months. Purchasing for mechanical can start October 1st for anything big that needs to be purchased very early, such as motors. And then Sierra's new member, CERT Rocket class, is going to start. We'll accept about 10, 15 new members or so. Sierra, being one of our level 2 certified flyers, is qualified to teach this class. I know Measle wants us to teach it in there, so it'll be good involvement for them as well. So we'll work with the new members, have them create an L1 CERT rocket over a couple months, and then their launch is November 20th. This is up at our LK launch site up in Clio, Michigan. It's a great site. I used it for my L1. And we'd be lucky to go back. Preliminary design review. This is going to be October 13th for electrical and 20th for mechanical. Purchasing will start the day after for electrical, and manufacturing and design changes will start the day after for mechanical. Design changes will be done by November 10th, and ordering can start for everything else. You see we have a week cut out for exams here, December 13th through 17th, where we don't plan on getting any work done this week as people have other things to do. We do still have a test launch, however, it is no longer in Kansas. It was in Kansas originally because it was a 30,000 foot test launch, which we don't need to have anymore because we're launching to 10,000 feet. So this is just going to be out in Muskegon, and it'll save us some money at this point in the year. So we're still going to have the test launch, but it will be in Muskegon. The Kansas launch will be after competition. That'll be the 30,000 foot launch. CDR will be March 15th and 22nd. We plan to come back to all of you and hopefully others with some good flight data, and hopefully our rocket didn't completely KATO. And if it did, then we have plenty of time to remanufacture it. We have another week set off for exams, as we're not going to get anything done that week because we have other things going on. Our final report's going to be due May 15th for the team. We'll submit it by June 1st or so, and then competition will be June 21st through 25th. Now I'll hand it over to Josh for the electrical team overview.
Okay, everyone can hear me?
Yep.
All right, so I'm Joshua Hawkins. This is the electrical team overview. We'll go over the electrical team structure, the systems that we'll be doing, standardization, which will be something I'll get into when I get there, and then the overall electrical timeline. Next slide. So here's the electrical team structure. You have myself, Joshua Hawkins, the electrical lead. For the data lead will be run by Thora BA. The RF lead will be run by Fadi Issa. The power lead will be done by Miguel Flores. On the data sub-team, we have Lucas Ringe and Batul Salmasi. On the RF team, we'll have Aaron Tevens, Matt Cook, and Albi Mulahari. And for the power, we will have Kyle Johnson. Next slide. Here's the electrical systems overview. Starting on the left-hand side, we'll have the Dart electronics. And starting at the top, we'll have the transmitter board and the PMS Mark III plus the batteries. And then slightly going down is we'll have the air brakes, the electronical version of the air brake systems, what actually opens and closes it. And then we'll have the ABC2, which will be what operates it. The Lapdog, which is going to be a big senior design project, which will then connect to some cameras and Raspberry Pi Zeros. And from there, we will have the seed board, which will be our experiment board, which is tied to the experiment. The big bus that's connecting them is just going to be a power connection plus a CAN connection. Then we'll have our completely separate custom GPS, and that will be going down to ground. It's completely independent from the other systems. For the booster electronics, we'll have an RRC3 altimeter. This is, again, this is separate from the RRC3 altimeters that'll be used for recovery. This is used as kind of an experiment. And this will be going to a mock RRC3 altimeter board, which will be something we'll try to do that have new members do. This will be going into basically the new member payload, which will have a flight computer or a power board, some sort of radio board, and then also in the booster we'll have an independent GPS. Then all of this will go down to the tracking antenna and dashboard. Next slide. All right, so for standardization, a lot of the mechanical people don't hear this isn't the biggest deal, but we plan on using the STM32s for our main microcontrollers all throughout the rocket because since we're all using the same thing, this will essentially the same thing. It will all speed up a lot of time it takes to teach the systems and then complete projects because everyone will have experience with it. It will decrease time rewriting existing software because pretty much no matter which microcontroller you use from this line, you can just transfer the code between them near seamlessly, which will make life a lot easier because you don't have to rewrite code. And it's a lot of easier design and manufacturing because there's a lot of documentation on these and there's a lot of developed software from ST that you can use for testing and manufacturing. Next slide. Here's the overall electrical timeline. Starting tomorrow and for about a month, we'll be going to research and schematics. Then after that, we'll have a month for routing, followed by October 13th, which will be PDR. Then following the day after that for a month will be purchasing, soldering, and testing. And then following that for the next few months up until electrical CDR will just be programming. And then after that, it's just going to be redesign until we decide to launch or competition. Next slide.
Hello, my name is Sarah Dormal, and I will be presenting the mechanical team overview. We'll be talking about mechanical team structure, the system engineering of the rocket, the CONOPS, and master distribution breakdown. Okay, so this is the mechanical team structure. At the top is me, Sarah Dormal, mechanical lead, and then the lead of airframe and propulsion is Andre Sturko, and the lead of payload is Logan Kilby, and then the lead for recovery is Alexander Burkhardt. An airframe propulsion team consists of Alia Sablini, Barnabas Tar, and Meredith Mon. And then payload team consists of Devin Nimmer, Dagan Marshall, and Shivani Patel. And then the recovery team consists of Carson Easter, Alexander Lazaros. Next slide. So this is the system engineering for the upper dart. At the very top, we'll have the custom GPS mounted above the payload and into the nose cone to avoid interference. And then below that is the payload. And at the sides there is the camera shrouds. They are located here to not cut into any coupler tube that will be present for breaks in the body tubes. And then the cameras are below the payload, but they are an entirely separate mount. The parachute for the dart will be located below a bulkhead and will cause a great shock to all the systems when deployed. Lots of forces. Next slide. This is the system engineering for the lower dart. So the air brakes are at the bottom of the arm, which is the top of this section, and they're at the center of pressure. The dart avionics will also be in the arm, along with the air brakes, and will be mounted on the rails. The arm is the avionics air brakes rotating mount, and that will just replace our flight package. And this motor tube will be empty to simulate where a second motor will be located, so that it'll have the correct impact on our deployable fins that a regular two-stage rocket would. The deployable fins fit around where there will be a motor tube, and the chord length is determined by the area left in the sides by the motor tube. Next slide. This is the system engineering of the booster. So the parachutes will create a big shock to all the systems when they deploy, but we'll have that connected to a bulkhead that will be protecting avionics that will be located to also minimize damage and dirt when landing. And then the motor's acceleration will create a shock on all systems. And the airfoil fins right at the end are mounted within the slots in the airframe and will affect the entire flight of the rocket. Next slide. So this is the concept of operations. To the left, you have a little diagram of what this all represents. So at 1A, our motor ignites. This is obviously at the very beginning of our launch, so time 0 and feet 0. And then about 3A, and after dart separation, we have booster apogee, which is occurs about 25 seconds and about 9,000 feet. 9,800 feet. No, yeah. And then about 5A, the booster will land with the booster flight length being about 70-ish seconds. At 1B, on the upper curve, the air brakes deploy, which is about 17 seconds into the feet and about 8,700 feet up in the air. And then at about 2B, the dart will hit apogee, and that's about 27 seconds into flight, and will be about 10,400 feet. And then after that, after parachutes have deployed, and the dart will land at 75 seconds into flight. Next slide. So this is mass distribution by rocket section for our 10K. Up on the left here, you'll see a breakdown by the weight of each major section, with a total mass of the rocket being 82 pounds. And then to the right, you see a breakdown by this pie chart to look at the approximate weight percentage of each section. And right now, the upper dart and the motor are fairly equal in sizes, which makes sense because we have to have weight up in the upper booster to upper dart to make it to balance the heavier motor at the bottom. Next slide.
All right. Before you start, Andre, I just noticed a couple people join. Rob, I know you joined, and I think Ben joined as well. I just want to specify something before we move forward. I specified before that we are launching to 10K this time, but the rocket is built to go to 30K and is two-stage. It's just the second stage will be empty to go to 10,000 feet, and we'll do a 30,000-foot test launch after competition. I just wanted to let you guys know now in case you got confused in a bit. But yes, Andre, you can go whenever you're ready.
Hello, I am Andre Shturko, and I am Airframe and Propulsion Lead. Here on the right, you can see projects that we are working on: General Airframe, Deployable Fins, Air Brakes, Project Lapdog, Goat, Airfins, and AARM or ARM. Please, next slide. So I will present the general airframe. So we will talk about general airframe, open rocket analysis, and camera shrouds. Next. So objectives, airframe encompass and protects a rocket system. Also, it provides aerodynamic stability during the flight. Next. So here you can see a preliminary Cata of general airframes. So there will be lower booster, upper booster joined by a coupler, and lower dart and upper dart joined by coupler and the nose cone. Next slide. So it will be one Karman nose cone and 4 body tubes, as I mentioned earlier. Since we are building a rocket that could potentially go to 30,000 feet, it's going to be bigger. So inner diameter will be 6 inches, and coupling tubes will be connected with one calorie friction, meaning from both sides of a joint, the coupler will be extended 6 inches as the diameter of the rocket inside. So on the right, you can see the table of lengths of the body tubes. So our total rocket's height is about 14 feet and 10 inches. Yeah, next slide. So we have done open rocket simulations, and right now our apogee is 11,000, more than 11,000, and flight time is about 74 seconds. Max velocity is 231 meters per second, and max acceleration is 63 meters per second square. So here on the right, you can see the graph of a flight simulation. So red is altitude, and you can see how the booster and dart separate. And dart continues to go to reach the apogee. Next slide. So here is early stability analysis. So competition requires that before and after motor burnout, we must have range of 1.5 and 6. And if it is not met, of the launch rod, it will be dismissed when velocity exceeds 100 feet per second. So right now our stability before motor burnout of the launch is about 1.7 and reaches 5.5. So there will be further analysis and the solidifications of the design, but that's what we have for now. And stability before after motor burnout is a range of 2.35 to 255. So you can see 2 graphs on the right that represent that. Next slide. So here you can see pictures of our open rocket, and blue dot and is center of gravity, and red is center of pressure. So on the lower picture, you can see our dart stage, and you can see the red dot, which is center of pressure, is exactly where we want it at air brakes, where they will be deployed. So yeah, next slide. So camera shots. This year we decided to keep similar design to what we had before, but just the diameter going to alter in the base to fit to our 6 inches diameter. So yeah, next slide. So camera shots will be made from student research and developed carbon fiber using vacuum bagging method, and we're also going to have acrylic window epoxy to to have additional structural support and protect the cameras more. Yeah.
Andre, you might be muted. I can't hear you anymore.
Can you hear me now?
Yes.
Yeah, sorry. So we were thinking about making round camera shrouds, but then experimenting with Open Rocket, we decided that we needed we needed specific shape of camera shrouds to move that pressure of point to where we wanted for air brakes. So we decided to go with square shrouds, so it's more like a fin shape. Yeah, next. And timeline, you can see there's going to be a lot of design revisions for camera shrouds after after manufacturing and test launch. Yeah. Okay. Thank you.
Right. So I'm Sarah Dolm again. I will be presenting for Barnabas Toth for the deployable fins. He was not available today. Just as a reminder, I was not the original person working on these particular slides. So if you have a question, just direct it to us, and we can either set up some sort of meeting later with Barnabas, or we can we'll try our best to answer that question. But yes, right. So. We'll be going over the objectives, the system module, a decision matrix, and the timeline. Next slide. All right, so the objectives of the deployable fins are to stabilize flight and to be highly reliable. Basically, we need to achieve a more efficient flight with a set of set of static fins, which requires a system to stay under a certain weight amount. And then the technology demonstrator for the airfoil and the off-center opening fin designs. The fins will open off-angle. Rotation will be shown later and will be countered with airfoil profile on the wings. If rotation is too sensitive to airfoil geometry, basically if we can't overcome the roll factor, we will go to a second plan B, which will have two sets of 3 fins that can be opened. Next slide. Right, so on the left here is Plan A, which will off-center opening fins. And you'll see a top-down version where you can see that the fins are not opening out to the side. This particular model is not yet pictured with airfoil fins. And then on the right side is a backup plan where we'll have 2 sets of fins that open up to try and to fix that. Right, next slide. All right, so the design strategy for the airfoil deployable fins will be basically we need to confirm that the CFD confirms that the rotation confirms rotation for off-center opening fins. And then if not, we can just proceed with the original plan. But if it does, then we have to check for how sensitive the rotational forces are to the airfoil geometry. And if it is not enough, then we will go with Plan B. Next slides. All right, so linear springs are going to be used instead of torsion springs for space saving. As you'll see in the picture below, they're not pictured in the CAT, but they are drawn in. And this will provide a better force curve and easier mounting. Spring strength can also be significantly increased if necessary. The fin holder arms are mounted in the bulkhead grooves, which will be CNC'd. Mounting is done with fasteners. And then the centering ring will be mounted on the bottom of the set bulkhead, and the centering ring will also be mounted directly onto the airframe. Next slide. So this is our airfoil manufacturing, how we plan about going to manufacture it. This particular picture is not size, though. So step 1, we will 3D print airfoil geometry and leave space for an aluminum core. And then we will wrap that 3D print, coat it with epoxy, and let that dry. And we will remove the 3D print and gradually fill in the gaps with pour foam. And then we will hold and insert the aluminum core into its proper position. Next slide. So this is decision matrix. This is basically the decision between having the off-center opening fins or having the 2 rows of fins. And basically the off-center opening fins they have a higher risk but more benefit. They could, and they are, they will fit very nicely, and manufacturing will be slightly easier than having the 2 rows of fins, which has lower risk but not as much benefit. So we're deciding to start off with the off-center opening fins. Next slide. So it's just the timeline here. From August to December, we'll be going over the initial undeployable fins designs and also concurrently doing analysis on that system. And then from December to February, we'll be doing design revisions depending on our feedback from design reviews. And then after that, we'll be doing design revisions from our feedback on our actual test flight. And then while that's going on, we have mechanical PDR here and PDR and CDR, and then we have a test launch in March, and then we'll have our manufacturing season from April to June. Next slide.
Hello, this is Adi Sublini, and I will be presenting about the air brakes. Next slide, please. So our objective for this year is to make a system that extends and contracts the blades to bring the rocket as close to target apogee as possible. If you look at the picture to the right, that is this year's iteration, we will be having similar design, like how it functions, right? It should be located at the center of pressure on the dart in order to prepare for the 30K launch. We are going to figure out ways to mitigate the frictional forces on the blades. We're looking into a ball bearing design on the bottom of the blade. We will be having weight reduction features to minimize the weight of the system, and we will be implementing a mechanical locking system. And the electronics mount will be the same design as last year, just scaled up to fit the 6-inch diameter instead. Next slide, please. So these are the weight reduction features that we desire for this year's rocket. We're going to give it a citrus/tomato aesthetic, as you can see here. So that is this design is from the, I wish I had it here. I forgot the university's name. One of the universities. I'll put it in the chat. And then that's the top view of the top plate, and then the top view of the bottom plate. Next slide, please. This is what we intend for the mechanical locking system. It will have 3 extension springs mounted to one extension spring mounted to each of the blades, and so that if the motor loses power, it'll immediately pull the blades back, and they should spring closed. Next slide, please. We were deciding whether or not to even involve the weight reduction features, and as you can see, the weight reduction features do in fact score a lot higher in the decision matrix, so it's the logical better choice. Next slide, please. So from August to December, we will be doing design and analysis, and then once we have our design reviews, we'll be doing design revisions, and as we do manufacturing, and then we will have a test launch in March, and then design revisions again, and then second manufacturing season ending on June 1st. Next slide, please.
All right. And now I am back working on a project this year, which normally, as some of you may know, we don't recommend. However, this, as Josh stated earlier, is a senior design project, so this takes the place of one of my classes. This is Project Lapdog. We're working on this with 4 people in total, myself, Matt Cook, and Lucas Ringe. We're all members of the team, and one other person that Lucas knows who's on the team for a little bit, Kai Leung. Lapdog stands for Long Range Air Brake Programmer and Data Ordered to Ground. So we're going to go over the objectives, the block diagrams, the ZenQ chip, which is our primary FPGA, and the radio front end. So the objective of this board, we handle all the calculations for the upper stage air brake system. There's an SD card for storing onboard sensors. It handles live transmission of camera video and other data to ground, which gives us part of our name. We have HDMI and speaker output capability, USB 2.0 connectivity, and this will serve after all of us are gone. As most of the electrical team is leaving this year, this can serve as a starting point for future electrical systems, especially with a lot of newer members coming in. And this can always be built off of in the future. And Lucas especially is going to plan on making some software foundations for these new members as well. And on the right is just a picture of the ZenQ dev kit that we're going to be doing some testing on. So this is the hardware block diagram. You'll see the FPGA chip, the ZenQ Z7010, is right in the middle. The 3 larger black lines, they're all buses, so just a set of signals, a set of wires. This is the same for the entire presentation. You'll see everything below the ZenQ chip. This is all of our radio front end, so our transmitter setup with our antenna. And then everything above is everything on the board, all the way up to the power and CAN connector coming from the PMS Mark III. And I'll hand it over to Matt.
Hello, I am Matt Cook. I'll be filling in for Lucas on this slide since his power is currently out. So the short version here is that we need to be getting data back and forth over Ethernet for getting some of that video data, as well as potentially in the future sensor data as well. So that he has put together some software for handling the TCP connection, and you can see a big old block diagram. The short version is it handles all the TCP stuff, and then he has what's called a publisher subscriber model on top, where you can subscribe to certain data that you want to get from like anything that's sending it to you, and then you have publishers that push that data to the subscribers. So that's kind of just like the general idea of what's going on here. You can go to the next slide. So here's the software block diagram for the radio. The short version here is that in the middle on the left, we have a finite state machine controller, which is handling all of the control signals for the system and determining whether we are currently transmitting or receiving, since the system is half duplex, as I'll go over later. And then on the top, you've got the transmit side, which is pretty simple. We modulate the data, we put it through a special filter, and then we output it over a digital to analog converter, and the analog front end takes care of the rest. And on the bottom part is a little bit more complicated, but the short version is that we need to equalize how strong our signals with an AGC. We have to do some compensation as well as some synchronization, and then at the end we can demodulate it using the same methodology we used to modulate it in the first place, and then we can give the data back and forth with the rest of the Zinc chip, which we'll talk about a little bit later as well. You can go to the next slide.
All right. And I'll talk just a bit about our ZenQ Z7010 chip. This is a BGA 400 package, which is a large package and a fairly complex package, being a BGA footprint. However, we do have some experience. Matt especially will be one of our go-to guys for getting this soldered onto our board. Everything else below here is just specifications for the processor. Most important things is it is a dual-core ARM processor, 32-bit, and runs at 667 megahertz. And this chip has actually already been ordered because it is very hard to find these days with the silicon shortage. And I believe that they should be at my house when I go back this weekend.
All right, hello, I'm back again. So here we have the RF front end. So I'm just going to give kind of the high level specs on how it works. So right now we're looking at around 8 to 10 megabit per second transit speeds without any forward error correction. And then it's currently going to be half duplex, which means that we can transmit and we can receive. We can't do both at once. We're looking to get around 27 dBm transit power, which for reference, the FCC legal limit is 30 dBm. So we're pretty high transit power for what we're allowed to do. We currently are looking around a negative 85 dBm sensitivity, and that just means what is the minimum power we have to receive in order to actually recover our data within acceptable error bounds. We're currently looking that without any forward error correction or a tracking antenna to get around 5 miles or so of range. And if we add in forward error correction and a tracking antenna, we can get potentially up to 30 miles of range. Next slide.
All right, and the decision matrix, we had a few different options. We've got Project Lapdog on the top, a Raspberry Pi and M2RB, which is the setup we're doing on Boosted Bear the next generation, and just a Raspberry Pi and simple telemetry. You'll see Lapdog is definitely the most difficult out of all of them. However, it does give us the most benefit, like I was stating earlier, with it being a jumping off point for future projects, which is why we chose it over doing a Raspberry Pi and simple telemetry. It is also fairly cheap, fairly inexpensive to us, as most of the cost should, hopefully, be subsidized by senior design budget.
Hi, I'm Josh again, and this is going to be the GOAT, or Global Operational Air Brake Tuner. Next slide. So the main objective of the GOAT is to operate the air brakes through use of a stepper motor. This will connect to the Lapdog both wirelessly and wired. It will receive most of its information over CAN, but upon rocket separation, it will receive it wirelessly. It is set up to be both wired and wirelessly in case the Lapdog board is not successful, from which this will be used as an interfacing board with some sort of Raspberry Pi or whatever solution we decide to go forward with that. Next slide. Here's the hardware system model. At the bottom, we have an STM32 WB wireless microcontroller. We have IMU, and then we have three ICs that will be controlled over SPI. We'll have a CAN controller and transceiver, a GPS, and a motor controller, which will be used to operate the air brakes. And then the air brakes will have a quadrature encoder that will feed back into the STM32 and will be used to determine the position. Next slide. Here's the active software loop. Starting from the far left-hand side, we'll have incoming data. It will be one of three types. It will be some ping confirmation, a sensor request, and an air brake request. A sensor request, it will pull the sensor data, perform error corrections, and then send it out. If it's an air brake request, it will just determine the desired position and then run a loop that will get us to said position, and then it will just send out information saying that it's done. And then for ping confirmations, it's to make sure that the CAN is still connected. Next slide. Here's the component deep dive. We'll be using the STM32 WB series microcontroller. It has an ARM M4 processor with an ARM M0 Plus radio coprocessor. It has a built-in 2.4 GHz radio transceiver, which will be used for close range Bluetooth throughout the rocket. We'll be using a TMC 261 motor controller, interfaces with SPI at up to 8 MHz, MCP 2515 CAN controller, and allow devices communicate over CAN using SPI. Next slide. We have then the TCAN 334 CAN transceiver. This is necessary in order to use CAN, and it just detects messages along the bus and sends them out. A GPS, as I want to state, anytime I have to mention a system like this is separate from both the custom GPS and the other COTS GPS we are using. The frequency that it's operating on will not affect any other outgoing frequencies on the rocket. This is a frequency that is used solely for GPSs, and it will be used to track the horizontal position of the rocket over the course of flight. Then a B&O 055 IMU. It's a 3-axis accelerometer with a 3-axis gyroscope and a 3-axis magnetometer. And on there it does some calculations for you, using all that data to spit out more accurate numbers. Next slide. There's a decision matrix. We had the GOAT, which has a risk of 4, difficulty 2, benefit 1, size 2, price 3, system engineering of 4, gets a rating of 66. The ABC, which was last year's board that fulfilled a similar purchase, had a risk 4, difficulty 2, benefit 3, size 2, price 1, system engineering of 4. And then there's the option of just having no air brakes, which will get ones across the board, except for benefit, which it will just have none of. Unfortunately, when it comes to systems like this, usually they'll score lower just because the innate risk when it comes to the difficulty of using air brakes to begin with, and also having to incorporate such a system into the rocket. Next slide.
All right, I'm Sarah Dormal, and will be presenting the airfoil fins as well. I'll be going over our objectives, system models, decision matrix, and the timeline. Next slide. All right, so the objectives of the airfoil aesthetic fins is to provide stable flight to the rocket, create a more aerodynamic profile to reduce drag at supersonic speeds, have an airfoil that is taller to reduce roll during flight, and to manufacture the fins in such a way to mitigate damage and the possibility of it breaking off when landing or during flight. To the right here is just a diagram with some airfoils examples. Ours will be similar to the supersonic interceptor up in near the top. Next slide. So this is the system model. This is just a side view here. It'll have a height around 6 inches. And then this is the side profile, the thickness. The thickness is not as much to scale. It will become thicker because we will need to put bars that will be inserted into the thin edge for structure support. And it will have a length of 12 inches. Next slide. So the airfoil will be modified, a modified supersonic airfoil due to the high speed the rocket will be achieving. The rhombus-shaped fins are rhombus-shaped fins, so much like ones that be on a plane, are much easier to model, but are can much more easily break. The trapezoidal-shaped fins, which we've been going with for years, will less easily be broken, but will be slightly harder to manufacture. Our team has yet to do any analysis on the airfoil shape, but I have read papers that have done analysis on the airfoil shape experiencing high speeds, and which it has influenced our early airfoil designs. Next slide. This is just our airfoil manufacturing. It'll be much similar to how the deployable fin airfoils will be manufactured. We have a 3D print that we will wrap with carbon fiber. And then we will remove the 3D print and insert the aluminum bars near the edge of the carbon fiber, near the edge of the fin, and then fill with pour foam or resin. Next slide. So the top two here are just a decision whether or not to remain with just regular trapezoidal static fins or to switch to airfoil fins. And our main reason for not going with airfoil fins in earlier years is because they were far more difficult to manufacture and to model. But now that we know how to do that, it is static. Now that we know how to manufacture and model them, regular static fins no longer provide enough benefit to outweigh the possible slight risk of doing airfoil fins. And then the trapezoidal, and this is the second half, is a decision between the trapezoidal shape and the rhombus shape. And basically, the rhombus shape has more risk involved with it. It is less difficult, but more risk. But we decided to go with the trapezoidal shape because it is safer. Next slide. And this is the timeline for the static fin airfoils. So for about from August to December, it'll be initial airfoil designs. And then from December to February, it'll be analysis on the airfoil shape. And then after our test launch, we may do airfoil revisions to maybe make it thinner or make it more angular. And then while that's going on, we have the mechanical PDR, mechanical CDR, where we will receive feedback and then also alter our designs from that. And our manufacturing season will be our later manufacturing season will be from April 1st to June 1st, which will put us right up to competition. Next slide.
Hello, I'm Andre again, and I will present the AARM or ARM system. Next slide, please. So this basically how we will connect avionics and air brakes to the frame, so it will allow us access to it. So next slide. So there will be 4 pins as on the right. A will be attached to the avionics and air brakes frame, and it will be inserted into the airframe, and there will be a bulkhead with the structures you can see at the B. So the pins will go into the wider holes, and then the whole frame going to be rotated 45 degrees clockwise to lock it in place. So that's how it will be attached. Next slide. So we were thinking of making like a wheel rail system where we would slide in and out the frame with avionics and air brakes like a drawer, but there were some risks factors and size problems, so we came up with this idea to fix it better. So that's our ARM project. Yeah. Next, please. So here's a timeline for the ARM. So we will design it from August until December 1st. Then the manufacturing season will start, and we will do design revisions. Then after test launch, we will do a second design revision and manufacture a new design. Okay. Thank you.
All right. And Maribeth unfortunately couldn't make it today, so I'll be presenting the propulsion slides. I've got 2 different propulsion systems to tell you all about. First, we have the 10K propulsion set and the 30K propulsion set, where we talk about some special considerations we have to have for that. So first, for 10K, we've done this before. We know how to do this. The propulsion system, it has to be able to exert the proper thrust to lift the booster and the dart. We're trying to get to 10,000 feet, so we want to get just over that so our air brakes can bring us right on the money. So single stage motor ignition, the current motor that we have is an N1100P from C-Z7010 Technologies. I know in the past we've used an M class motor, and I know the concerns about higher impulse motors and higher class motors are much more expensive. This N we found was within our price range, with a total impulse of 14,000 Newton seconds, pound seconds in the parentheses, and 98 millimeters in width by 41 inches. For 30K, we have 2 motors that we need because it's a 2-stage rocket. Just to clarify again, that this launch will happen after competition, so after we've launched a 10K with the N1100. So the same goal with this propulsion system. However, in the booster, we're going to have an O3400, which I know an O really gets up there in terms of cost. I would expect an O to run about, $3,000 to $5,000. This one was $1,600, so a steal in my book. Total impulse of 21,000 Newton seconds. And then the Dart would run an M2500. The reason we chose this motor in the Dart was because we already have one, which saves us a good amount of cost going in. And that has a total thrust of 8,429 Newton seconds. Separation of the booster and the Dart. This occurs after the first stage motor burnout, which you saw in the ConOps. This is the burnout of the O3400 motor. One thing that we have to think about is the upper stage ignition system. This is an air start, which is much more complicated, I know, as Robert would tell us. I'm looking forward to the feedback to hear about some air starts, as we haven't done one before as a team. I was doing some looking at the competition documents. A COTS flight computer is required for second stage ignition based on the latest version, the latest revision of the DETG. This is section 5.11 titled Air Start and Stage Flight Computer Requirements. We've got some options here. I've looked into a few of these options, such as the MASA-54 or the Altus Metrum Telemega. We already use some products from Altus Metrum, so that could be one of our best choices, as well as some of the MARSA systems flight computers looked interesting as well. We were originally looking into SRAD options for this. However, they are explicitly disallowed by competition in that same section. Now, one thing that I've never done an air start before, which is why especially I'm glad that Robert, you came so we can ask you some questions here. It seems the only way that I can think of igniting this would be to have the flight computer on top of the motor. The air brakes are also up here as well, so this is a busy section of the rocket. And remember, the deployable fins are on the side of this motor, so there's a very busy portion of the dart. I have wireways on the outside of the motor tube. This is a fiberglass motor tube. And then just out and in for the igniter tip to go all the way reach to the back of the motor. I was hoping that they designed motors especially for air starts where you could just put it in the top so we wouldn't have to run an igniter all the way down and all the way back up. But it's really hard to find information on air starts online, so I'd be grateful if you had any comments on that near the end. But yes, that's all I have for propulsion. Logan, I'll cut you off here a second. It is 7:09. We've been presenting for just under an hour, so we'll give everyone just a bit of an intermission, 5 to 10 minutes or so. And then we've got, I think about 60, 70 slides left, and then we'll be open for questions. All right. Well, I think just about everybody's back, so we can get started here. Take it away.
Hello, I'm Logan Kilby. I'll be presenting for Payload. Next. The main purpose of our CubeSat payload this year is to house the flight data electronics as well as the experiment. We'll also be able to monitor the conditions of the rocket visibly using cameras which will be separate from the payload. In addition, during and after the flight, we'll have the ability to track the position of the rocket using our custom GPS, and we may also have a backup tele-GPS. Another feature of the payload will be to balance the rocket to achieve a more stable flight. Next. The payload frame will consist of 4 ribs welded to 4 bulkheads. We are considering slotting the ribs to hold the board stack. To allow clearance for electrical, we will have wireways milled into each bulkhead. For easy assembly and installation, all of our mounts will be secured to the ribs instead of the bulkheads. And we are considering using a heavier metal to act as sort of a ballast for our and to meet our 8.8 pound requirement. Next slide. The camera mount will be separate from the payload, but it will be located just beneath it. And it should move in and out of the rocket, and that will allow us to easily slide the body tube on and off. The mount will be milled from aluminum to minimize any kind of slop or offer a more robust design, which is important so we have a clearer picture during flight. Next. Our experiment will be analyzing microorganisms in soil. We want to run at least 4 sections of dirt in test tubes with screw caps. This will minimize any kind of risk of failure in one, and so we'll get solid results. Next slide. Our plan is to have our design done by November, and that's when we'll start prototyping some of the mounts. And during this time, we will purchase other materials that we need, and we hope to begin fabrication during November through January, and this will allow us enough time to find any problems. Next.
Hi, I'm Thora BA. I'll be presenting the seed board which is this year's electrical system for the payload experiment. Next slide, please. So up in the top right corner is one of the sensors chosen, the CO2 sensor. But the objectives of this board is measure the soil characteristics throughout the flight. So we're measuring CO2, humidity, pressure, and all those good things. And pH is happening before the flight, so that's not part of this system. So we're going to send that data over CAN, and then hopefully that data will support this year's payload experiment. Next slide. So this is the system model block diagram. So all the sensors will communicate over that bus to our payload MCU, and the payload MCU is also going to be an STM32 MCU chip, like the other boards in the electrical systems, and then that just connects power and CANs like to the other side. Next slide. This is for software. We're just gonna collect sensor data, do some compensation, like for it, the CO2, form a packet and send that data to CAN. Next slide. So that image in the corner is our pressure sensor. So this pressure sensor, we've used it last year, so that's why we're going to use it again. So we have it in stock, so it won't be expensive. For the CO2 sensor, the SD-CD30 sensor module, those are a bit more expensive, but you're getting a good reading on the carbon dioxide compared to other sensors, and also their availability. Next slide. So for the decision matrix for this system, you can see the pH sensor probe was not super, wasn't the best choice to include due to its size. So that's why we didn't go with it, even though the benefit was there. The CO2 sensor block, it's also a little bit more pricey, but compared to the size of the pH sensor is smaller. And then third choice was also looking at spectroscopy system setup. And that setup would be way more expensive, and also size is pretty big. And it's something we haven't done before, so the difficulty was higher. Next slide.
Hello, everyone. My name is Miguel Flores. I'll be presenting the PMS Mark III. Go ahead. So the PMS Mark III is responsible for powering the DART's electrical systems, excluding the GPSs. PMS can receive charge through wired and wireless means, and the PMS is responsible for powering Lapdog, Seed, and the GOAT. Next slide. So we're just going to read this system model from left to right. So we have our external power. It's AC power, giving power through a primary copper coil that induces a magnetic field, and then in return creates electrical current in the secondary coil. That goes to the receiver and full bridge rectifier, which then in turn goes to the charging IC and then powers the battery. And then beneath that, we have the USPD, that's USB power delivery. That is just our wired charging. And then from the battery, it will be balanced and go to the power and CAN. And on the right side, we have the temp sensor accelerometer feeding in data to the microcontroller, and the microcontroller is sending data over CAN. Next slide. So the charging IC is going to be the same as last year. The balancing IC did change this year. It had to be capable of balancing 3 cells. The MCU will be the STM32, as Josh mentioned before. Next slide. So the batteries that we have chosen this year are the Samsung 18650 lithium-ion batteries. They will be configured in a 3S2P battery formation, capable of 7,000 milliamp hours and 10.8 volt nominal. The receiver IC, responsible for receiving AC power from the transmitter board. The transmitter IC is just capable of transmitting 15 watts of power, which is the same as last year. Go ahead.
So a few things we're looking at here is the inductive charging versus the wired charging. So ideally, wired charging is the optimal solution. The inductive charging, being the wireless, is just a secondary form of charging, which is nice just in case. And then we have the PMS Mark III being compared to last year's PMS, and ideally we'll be using the PMS Mark III this year, and that obviously scores the highest. Go ahead.
Hello, I'm Sierra Stockwell, and I will be presenting the new member payload with Joshua Hawkins in place of Kyle Johnson since his power is currently out. So here is a preliminary model of what the new members might be designing. Obviously, we're going to let them take it in their own direction. The point of this payload is to allow members to create their own experimental payload. They will have constraints given by us so that it doesn't impact our open rocket at all, with a maximum mass of 4.4 pounds, which is half of our minimum mass for the typical payload submitted for competition. So it just gives them an interesting constraint and allows them to think about how they can limit weight. And where our CubeSat will be 4x4x12, which is by competition rules what we would typically submit as a CubeSat, theirs will be 4x4x8, again to have them work within a smaller constraint since this is in the booster. Our new members will gain autonomy over their project by developing their own payload experiments, so we haven't set out what they will be experimenting on yet. That will be up to them. Again, just within the constraints, and electrical new members will design their own simplified version of the flight computer. Mechanical new members will design a CubeSat frame and electronic mounts within constraints. And since this is really a payload member and electrical member task, our certification rocket class will mainly pertain to recovery and airframe new members in the fall. Here's our system diagram. As you can see here, it's a very simple CubeSat to allow them to really focus on the details and staying within those constraints. We have power, a flight computer, and our experiment, whatever they decide that will be, and they get to play around with what materials they use to build this CubeSat.
All right, so for the, okay, just make sure that's right. So here's the electrical system diagram. So as Sierra's kind of mentioned, this was meant to be pretty open-ended, and it's mostly up to what the new members want to do. But kind of as a general layout is what we would think are some of the things we'd want as guidelines. We'd want some sort of power board, some sort of radio board that sends information to ground, and then obviously some sort of experiment board that's meant to interact with the experiment that they choose, a flight computer that's meant to log all of that data, and then we're going to try to see if they can do like a mock altimeter, which would be kind of to simulate what the RRC3 altimeter does, at least in terms of just determining what elevation we are currently at the time. And at the same time, it will interface with an RRC3 altimeter because those altimeters are able to actually output their current information. Like it's able to output current height, temperature, and a few other things, but it'd be something nice to, in theory, just compare, see how close they get, and also just nice to have like actual numbers in real time. Next slide.
Josh, one thing I want to mention before we move on to the slide. This RRC3 altimeter is not a recovery altimeter. This is a separate one that we've included just for this experiment, or just for this payload. Nothing will be interfacing with the recovery systems other than the recovery systems themselves.
Yes, that is true. I forgot to mention on this slide, but I did make sure to mention it on the big electrical systems over here. Thank you, Justin.
Great, thanks.
Then for component deep dive, since this is mostly open-ended, here are just kind of some suggestions that we would recommend. We recommend some STM32 microcontrollers as they're trying to make them standardized, buck converters for power, temperature sensors, accelerometers, and a pressure sensor. Obviously, a lot of this is open-ended. This could be changed. This changes depending on what they're trying to work with. Next slide.
Here you can see our decision matrix, just weighing the benefits and risks of the new member payload. There aren't many risks since we are constraining them to a mass that we've determined is appropriate for our rocket. And it has a bit more difficulty, but that difficulty is the purpose, to teach members how to build a payload and to feel like they have a connection to what they're doing. Here's our timeline. So in the first few weeks of new members being onboarded, we plan to have initial design training. So we'll have a few weeks of just, here's how you do CAD, here's the basics of what you need to know about materials that we could possibly use in this. And on the electrical side, I'm sure they will also have just basics of how their boards go. And then October 22nd through November 12th, which is about their second month on the team, will be when they begin their first design iteration. With new members, there's always going to be a lot of design iterations, and we really want them to experiment with what they feel is right in this payload. So they'll create their first iteration. We'll have an internal new member design review so that they can learn how to present in a bit of a less stressful environment than a typical design review, since they will be joining towards the beginning around when we have our PDR. So this will allow them to get that feedback and then to go into their second design iteration phase, which will then lead them into their first manufacturing season. And then that will lead to our test launch. And after that test launch, they will see if anything needs to be changed in their designs, and then if anything needs to be changed in manufacturing, if there were to be some catastrophic event or anything with our rocket, or if they decided that their design didn't work.
Hello, this is Alex. Oops. Hello, this is Alex, and I will be presenting on recovery conceptions. Next slide, please. To begin, just to reiterate, I hope we all understand how parachutes work, but if there's anyone here who doesn't, here's how they work. They allow us to control the terminal velocity of whatever vehicle they're attached to, and we need that because fiberglass vehicles are pretty heavy and they can pick up a lot of velocity and momentum on their way down to the ground, so they can hurt people. So we need parachutes to make sure everything's safe. Also, we want to make sure that we can actually recover our vehicle so it falls relatively close to where we launch it from, which is part of the reason why we use 2 parachutes. Now, we hope to use 1 parachute with a reefing system, which would have 2 effective projected areas. So it would fulfill the role of a drogue parachute and a main parachute. The first parachute, known as the drogue, slows down the descent vehicle and stabilizes it, and the second parachute drastically slows it down to its final terminal velocity. Next slide, please. Our booster systems consist of 4 missile work altimeters. Now with a 30K rocket, we would be breaking the sound barrier, so we would want to use 4 RRC3 altimeters because they are Mach proof. Now with this iteration of the rocket this year, we will not need to do that, so we will be using 2 RRC2s and 2 RRC3s. The RRC3s will go on the Dart and the RRC2s will go on the booster. Now, if the reefing system is successful this September, we will try to implement that system in both rockets. So we will have 2 identical parachutes with eyelets for the reefing line, and the only difference between them will be their size, because the booster and the Dart will have different masses. The Dart will be a lot heavier. Now, if testing, or our September flight rather, is unsuccessful, we will have to rework our reefing system, or we will pursue a drogue and main parachute for each or one of the vehicles. We may do the same thing as this time, where one vehicle has 2 parachutes and the other vehicle has a new reefing system. Next slide, please. the avionics bays for the recovery systems will not change much at all. However, we are setting out a few standards going forward. Now, the avionics bays house the recovery electronics, the aforementioned altimeters. Additionally, the booster will house, or rather the booster recovery avionics bay will house the booster GPS and its power source. Other than that, that's all they house. There is some extra space, so we could potentially house some more stuff if some other systems close by need some space. But as of right now, they will only be housing the altimeters, their power sources, and in the booster's case, the GPS and its power source. Now, the standards that we wish to lay out this year are that the designs of avionics bays need to be or will be easy to manufacture, prototype, and integrate. Now, part of this is that all designs will be made with the intent to 3D print all of the parts, because filament, plastic filament, is a lot lighter than sheet metal or any milled metal or aluminum or steel. And they're a lot easier to manufacture because we don't actually need access to campus. All we need access to is a printer. And if we don't have printers to use at home, we can still use them at MESL by sending files over to the people who work there. Retaining hardware will be used, things like steel bolts and the like. And the main constraint is that they are going to be interfaced with the threaded rods that will go through the system. And a similar system to what we will have is depicted in the right pictures. Next slide, please. The ejection charges we will use this year will be 4F black powder burrito charges. Burrito charges will be used for ejection and separation charges. So this includes separation of the dart from the booster, as well as the ejection of the sustainer from the flight package, which also deploys its parachute. The black powder charges will also be used inside of the tender descenders to activate them, which will not have a burrito charge, but it's a similar idea where an E-match ignites black powder, which causes something to happen. Next slide, please. The timeline for recovery this year, as you may see, the design will go all the way through, because design, of course, is an iterative process, but specifically with recovery, we need to test everything before we can show up to competition and launch our rocket. We have to have video evidence. So if anything is wrong or if anything needs to change, we need to change the design. We may need to alter some bays as we iteratively prototype them. We have in the past. So that's going to go all the way through. Now, we will prototype and test starting December 2nd. I hope to have new members working on a bunch of designs in the fall so we can start to print them and apply them in the next semester. We will also need to do a lot of testing early on when there's still snow on the ground. I'm sure the Dearborn Police Department will be happy to help us with that. And of course, we have the test launch in March that will happen, and by then we will have already ground tested several recovery systems. Starting in March, we hope to start the final manufacturing, which means we're going to print off the final iteration of our avionics bays. We are going to set up the final iteration of our shot cord lengths and all of that stuff. Additionally, we will be sewing together the parachutes, which will have been sized because all of the masses should be in by that time. And of course, on June 5th, we will have reveal day where we will show our rocket and all of our systems together. And with that, I believe it is the end of the recovery section.
Hello, I'm Fadi Isa, and I'll be presenting the PIG board, or the Programmable Independent GPS. Next. So the PIG board is the GPS that we're gonna research and design. It will transmit on the 400 megahertz ham band, and it would also be supported by the tele GPS, just in case our custom GPS fails. We don't lose our rocket, basically. And the board itself could be used as a receiver or a transmitter. Next. So the custom GPS is independent from all other parts of the rocket. That's why it has its own power source. It also has a battery protection circuit, a buck converter, and all the GPS data will be sent to the microcontroller and it will be transmitted to ground. The ground receiver is basically the same board, but it will be receiving data and showing it on the computer in a way we can understand it. Next. For the software, the microcontroller is going to read the GPS data, convert it to IPRS, and it would transmit it to ground. Next. The microcontroller we're going to use is the STM32WL, mostly because it's standardized across the rocket and it should be pretty easy to program. As for the GPS receiver, we're going to use the MAX 277, kind of because it's the same GPS that the GOAT uses, and it also uses the SPI communication. Next. So our custom GPS with the tele GPS is the second one, and on the bottom two we have the big red B and the featherweight, which are other Cata options. But the reason we're not gonna use those is basically because first, it's very expensive, and we've never actually worked with those, so the risk is a bit higher, but not as high as the pigboard by itself because we've never done it and we don't know if it's going to fail, and the last thing we want is to lose our GPS. While the pigboard plus the tele-GPS has the same score as the tele-GPS, I think it would be much better if we go with the pigboard plus the tele-GPS just to expand, our knowledge and get out of our comfort level, basically, because we already worked with the tele-GPS, and the risk should be pretty low because, again, we have the tele-GPS as a backup just in case it doesn't work. Next.
Hello, I'm Matt Cook. I'll be talking about the tracking antenna board. You can go to the next slide. So the main objective here is that we want to actually track the rocket with this antenna during the launch because we can use high directional antennas to get significantly increased range as a result. And for clarity, this is solely for getting data from Lapdog, not with the independent GPSs, because that would significantly increase the risk in case it failed, and we get very little benefit because the GPSs already have an insanely high range anyways. You can go to the next slide. So here's the basic block diagram. The idea here is that we have multiple antennas on a mount coming in. We've got some power detectors, and then that result gets fed into a microcontroller, which drives some steppers. And the idea is that the microcontroller compares the received power from multiple different directional antennas, and whichever one is pointing closer to where the signal is coming from is going to get a stronger signal. So between three different antennas, we can estimate the direction of the signal and point the tracking antenna in that direction using the motors. You go to the next slide. So here's a software diagram. It's nothing complicated here. We get the signal strength with some ADCs, and there's going to be three antennas because that's what you need in order to get both left, right, and up, down with a setup like this. And then we use that those received signal strengths to estimate the direction, and then we update our position, and then we take more strengths and we keep updating it until we are pointing as close to the rocket as we can be. You know, next slide. So right now we're just looking at using some analog devices power detectors. Namely, they have a very high dynamic range, and this just means that we will get accurate readings whether we are getting a high power received or a low power received, which means the tracking antenna will be able to adjust itself whether the rocket is close to us or far away from us. And additionally, the analog devices power detectors are very cheap and work on a lot of different ranges, which makes life easy. You go to the next slide. So here's the decision matrix. Our choices that we could either make a tracking antenna or we could use a dipole. Tracking antennas are a little bit riskier because obviously there's a chance of failure. However, if things aren't working out in testing, it's not exactly expensive to fall back on just using a dipole. Obviously, it's harder, but we get a lot of benefit out of the fact that we get a much longer range. Both options have the same size because it's not on the rocket, so size isn't a major concern. And obviously, downside is the cost is going to be significantly higher than a dipole. You can go to the next slide.
Hi, my name is Erin Stevens, and I'm going to go over the dashboard. Next slide, please. So the dashboard is the ground software for receiving data from the rocket. It started development with Boosted Bear New Mexico Drift, which was the 2020 rocket, and it's continuing for both H.A.S.M.A.T and Boosted Bear the Next Generation, the previous rocket that we're currently working on at the same time. So its main objective is to receive GPS data from the rocket for recovery, with a secondary objective being receiving all the other data from the rocket, most notably the live video. There's a few major changes that need to be made for H.A.S.M.A.T, mostly focusing on the data client. So most of the backend should remain the same. Next slide, please. So here's the software block diagram for the dashboard. Data comes in through USB ports on a computer, and that data goes to the data client, which then sends it to the data server using TCP and IP. Data server puts it in the SQL database, which is where it's read from to make the display on the web front end and web back end. Next slide, please. As you can see, it's a little bit less risky to be doing the dashboard than local software, because local software is only saving the data locally. And if there's a critical failure with the local software, we would lose all of that data. But it's a little bit more complex system engineering. So that's why we went with the dashboard, but we have that local software option to back up to if we need to. Next slide, please. And here's the timeline. We're currently working on the development for Boosted Bear the Next Generation, which will also contain development that we hope to use for H.A.S.M.A.T as well. We're hoping to switch over to H.A.S.M.A.T development by September 1st, and that's all those data client changes mostly. And concurrently do testing and bug fixes for the Boosted Bear the Next Generation and development in time for the test launch. And then after the test launch, we're looking to move to testing and bug fixes for H.A.S.M.A.T. It's a pretty tight schedule, and this is subject to change depending on what happens. Next slide, please.
All right, we've reached the project management section, so we've just got a couple things left, and then we'll start taking questions. So I'll present this project management. We've got some project completion numbers for mechanical and electrical, and some other cutoff dates, and a descope for projects. So first, we want to look at project completion. Design season has not started yet. These are very rough numbers from our work breakdown structures that were just completed. So you'll see we've got the different projects for payload, airframe, and recovery, with critical project time and overall project time at the bottom. So critical project time for research and design of 135 hours, overall project time of 510, and for manufacturing is 285 for critical, and 998 hours of manufacturing overall. These numbers have a bit of a range to them on whether they're high or low, as they're all just estimates. We hope to refine these estimates, especially next year, after collecting data on how much time we actually spend on things. For electrical, it's a very similar story, where we have numbers that are either too low or too high. We have 68.25 hours of critical project time. This is solely for the PIG, which is our custom GPS, but remember there's always the fallback of the tele-GPS. Overall project time for design of 1,400 hours, manufacturing time of 500 hours. Some critical project cutoff dates. The second stage motor cutoff date was September 25th, which is our test launch, but we'll talk about that in the next slide. This would be changing the 30K rocket into a 10K rocket. This would keep the rocket the same as we've already done, just changing it to one stage. We've got three other things occurring on January 15th of next year. That's air brakes, deployable fins, and airfoil fins. Analysis is going to be complete by this time, and we're going to determine whether or not these options are viable in our current rocket. So for air brakes, the air brakes would be removed if they were not able to work cohesively with our rocket, and this could indicate a motor change. The deployable fins, as Sarah stood in for Barnabas earlier and talked about, the first design for deployable fins is the off-center opening fins. The second design for the deployable fins is two sets of 3 fins stacked on top of each other. And the final thing to fall back on would be second stage static fins. For airfoil, the backup is just regular static fins as we've done in the past if we figure out that we either A, can't manufacture the airfoil, or B, they do not provide us any benefit to our flight characteristics. March 15th of 2022, we can cut the custom GPS. Being that we already have a backup in the works, this cutoff date does not have any major impact on our systems, except for the fact that the holder for it would be empty in flight. All of the in-flight testing will be done, and the ground testing will be done. And if it doesn't work, then the tele-GPS. However, if we're able to make changes to it in time, I don't see any reason why it couldn't stay in the final rocket, as it doesn't interfere with the tele-GPS at all. Project D-Scope. Normally this would be something that we include in design reviews further on, but we have already had a couple projects that we've had to cut. The first one was removed yesterday, August 10th, the second stage motor. As I talked about in the start of the presentation, going to 10K instead of 30K is a lot easier on our members and our timeline. However, keeping the project so that it can go to 30K, so that we can do this test launch in the summer to 30K, is very good for us as a team. This means that we can effectively use this year's competition rocket as a test rocket, as a jumping off point for next year. Which, I know that people, really want to go to 30K, and it's one of our big goals as a team. But we need to work our way up. COVID has set us back a good ways, and we want all the experience we can get before we go up there. Our next project that we cut was the angle of attack sensors. If you remember, the pressure sensor ICs in Boosted Bear, or two Boosted 2 Bear rather, did cause severe severe damage to the rocket, especially to the payload. This year, there was a different idea for angle of attack sensors. However, we realized that even though they're smaller sensors, they could cause flight instability, and there was no real way to connect them to the outside of the airframe, as they couldn't be covered in epoxy because they are pressure sensors, and so they would shear off in flight either way. The alternative for this, no alternative, just cutting the system.
Hello, I'm Sierra once again. I will be presenting our financials. And before I begin, there may be a little bit of sticker shock, but I will explain. Okay, so here's our budget overview compared to the last budget that we had when we were in person. So this was back in 2019-2020 year when we were planning to launch to 10K. Reminder, this rocket is a 30K rocket being put into a 10K CATS competition, and our team has been growing. It is mainly the fact that our team is growing that has pushed our budget so much, because in the past we have only budgeted for 20 members to go to competition. Even in the 2019-2020 year, this was a very difficult thing for us to deal with. There were many hard conversations being had about who might not be able to go to competition and who should go to competition. And we don't want to have to do that this year. We would like to bring everyone on our team with our growth and with our planned growth. So this year we're planning to have at least 40 members go to competition. With this, and well, I'll explain more in the next slide, but with this and the 30K plan, the plan for the launch after competition in Kansas to 30K, that brings up our finances substantially. As you can see here, major increase in business. That is, again, because of that increase in members and because of travel expenses for going to Kansas and for going to Spaceport America Cup with more members. Airframe and propulsion has gone up considerably because we are both making a larger rocket with larger body tubes, and we are also using many motors. So we want to have a test launch in March in Muskegon for this rocket before we go to competition. So that's a motor, then competition is a motor, and we have a backup motor plan just in case something happens like it has in the past where maybe purchasing doesn't come through in time, etc. And then in Kansas, we would need to purchase 1 or 2 motors depending on if our current M2500 is still up to par. So that is where a lot of that expense comes from. And then you can see recovery has decreased because in the past we have over budgeted in recovery, but lately we have looked at what we actually purchased in previous years for recovery and adjusted for that. Payload mechanical has decreased because our payload has gotten substantially smaller and a bit simpler, going to CubeSat. And we also have a less expensive payload. Back in this time, we had a bunch of pressure sensors that we were still purchasing for an internal sensor panel array, which we no longer have. So this experiment is a lot cheaper. In terms of electrical, some boards have, well, all of our boards have gone down because back in 2019, 2020, we were really trying to make, well, things have, I think our electrical team has gotten better at determining prices, and we also have materials from previous years that we're reutilizing on these boards. So prices have gone down there. And that is how we come out to $52,791.47 currently. Next slide. So here is my budget plan of attack. The key reasons, again, for the increase in budget are planning to bring 40 members to competition instead of previous 20. We also plan to bring 40 members to Kansas, which is another reason why that trip will be expensive. Housing and gas price has also increased since the last time we traveled. I know, Trent, you have also looked at Airbnbs since our last time traveling, and it has gone up. And hotels have gone up. Gas prices have obviously gone up post-COVID. So a lot of things are shifting, and we need more housing as well for 40 members. So that is why the price has increased so much there. And then the 30K launch in Kansas after competition, again, means more motors and more travel costs. The team will request $30,000 from CCS, which is the most we can request. And we also plan to request $20,000 from the Woods Foundation, where we have previously gotten a sponsorship before of a similar amount. And we plan to use remaining funds from this current rocket, if we have any, fundraising and or additional sponsorship to cover any additional expenses. Competition housing, and also another nice thing about going to 10K COTS category with a 30K rocket, if for some reason we aren't able to get the sponsorships that we need to go on that trip to Kansas, that could be cut from the budget if needed. Competition housing is estimated to cost $11,000 for 40 members, including hotel stops on the way to and from competition, since it is a very long drive and we don't want anyone to potentially hurt themselves driving that long. We've had some close calls in the past with very tired drivers, and we don't want to risk that again. Gas to competition is estimated at $8,000. Kansas hotel rooms will cost $2,200 for 40 members to stay 2 nights, and the gas price for Kansas is estimated to be $4,000, and that is taking 8 to 10 vehicles, depending on what vehicles we have available to us.
All right. Well, thank you everyone for joining us. The obligatory shout out to our YouTube channel, MASA-Dearborn Rocketry, if you'd like to see any of our launches or other design reviews or SAC competitions. Now we're going to have our question period. I think what I'm going to do this time is I'm going to go down the list of guests and see what comments everyone has. I know, Andrew Gilstrap, you're first on the list, and I know you like to go last. Would you still like to do that today?
Yes, I'll hold comments and maybe jump in if there's something I'd like to comment on that someone else comments on.
All right, sounds good. Our next guest is Andrew Johnson. Thank you for coming. He's the president of ISC. Did you have any comments for us at all? Any questions you'd like to ask?
No, I thought the presentation went well, and yeah, good job.
Well, yeah, thank you so much for coming. I don't think we've had an ISC member here before, so we appreciate it. If you ever have any design reviews or anything, please let us know, and I'd be happy to come.
Awesome, will do.
All right. Thank you, Josh, for linking the MASA YouTube. I'll go down the list a bit. Ben, any comments from you at all on the presentation? Any questions you have?
I got a list of questions, yeah. So if you want me to,
Sure.
sprinkle a few in or just go down the list here.
Fire away. We'll see how far we get.
All right, this is kind of just how I was looking at it. So you guys are talking about for the deployable fin system doing some off-axis deployable fins.
Mm-hmm.
Have you guys looked at the relationship at all between the lift generated or that you're trying to generate by airfoiling them and the rotation caused by, you know, the fins being off-axis? Because at some point, you know, you're going to have your speed is varying, so your lift is going to change throughout your, you know, dart or eventually boosted flight. So that number is not going to be a constant. There's going to be some equation there that you're probably going to have to consider.
All right. And unfortunately, Barnabas wasn't able to join us today, and he's been working on deployable fins for a while. I'll give it my best shot here. So yeah, one of the first things we considered with off-center opening fins was the rotation factor, as roll rate can be, you know, it can increase very significantly with fins, even just standard fins being off-center by just a little bit. So we definitely want to run enough CFD to where we want to ensure that there's no issue at any speed. But obviously, yeah, we'll have to look into that more and see if there's considerable benefit from the airfoil versus the rotation. Sarah, did you have anything to add to that?
No, that pretty much covered it.
All right.
I'll just jump in real quick too.
Sure.
Ben might have probably will mention this or would have mentioned if I didn't jump in. But as a note too, you basically also lose effectiveness of the height of your fin. The more of an angle you basically kind of put it at, you know, off nominal or off normal, because it's getting, you know, the same distance is not getting you as far out into the airstream. So you lose effectiveness. So to achieve the same kind of, not even considering roll, you know, to get the same kind of stability, you need to be, you know, maybe like 25% or like 30% or maybe 50% longer of some kind, or, you know, just overall scale of the fin to be able to generate the same kind of just regular static stability, which, you know, which might be, you know, somewhat accounted for by if you let it spin stabilize, but that's a whole bag of worms that you're trying to currently avoid.
Right, and we'll have to see what sort of size we can get. I know the big constraint there will be the size of the slot in the airframe. So we'll just have to see how much length we can get out of those.
Well, though the good news is that currently there's nothing above it, so we definitely have room to make them larger. We would just, you know, have to consider, like Justin said, the size of the opening that we have to be creating for it.
All right. What do you have next for us?
So same vein right now, but you know, off-axis fins are going to behave differently than normal at angles of attack as well. So just something to, you know, consider down the road. I know it's early for that, but they're not going to behave the same as you would expect for normal straight fins.
All right.
So if you can go back in the slides a little bit too, I don't know what the plan is for, you guys are talking about linear springs for the deployable fins, and
yeah, I was quite confused on this one too.
Yeah.
I don't have any information on the type of spring that we're using. Sarah, you'd be the next in line if Barnabas has talked to you about it at all. But otherwise, we'd have to talk to Barnabas.
I don't know very much about it.
All right. And what's your concern with linear springs?
Well, I mean, I was looking at the picture on the right with the squiggly lines drawn on it, and to me, that would not be an extension spring. That would be, you know, a spring in tension, which would not open it. And you're trying to rotate something, which can be done with a linear spring, but I just see an issue with packaging. So I was just hoping for, you know, maybe an explanation of what the plan was there.
All right. I'll have to talk to Barnabas specifically. Sierra, do you remember if we used linear springs in the past for this last year's deployable fin system, or if we used something else?
No, this was something that he wanted to implement specifically because he didn't like the way the springs were this year. That's all I really know, is that he really didn't like having the springs where they were, how they were, but I don't know exactly what his thought process was behind this.
All right.
Yeah, the only thing I can deem from this is, like, in this current position, if it is like a compression spring and it's just like compressed, then it just keeps the fins closed during when it opens, and just nothing happens because it keeps the things inside the rocket. If it's like an extension spring, it can like pull like the fin part way up, but then it gets to like a asymptote of its like motion range that it can't do anything with, and then it all relies on drag from there to be able to pull and work against the fin or work against the spring. So it just seems a little odd, is all.
All right. We'll definitely have to talk to him about it, and then we can get you an answer on that. But thank you so much.
Next item. I think it's an Alia question she was presenting for the air brakes.
All right.
You mentioned roller bearings. What's the idea with roller bearings here? Or ball bearings? I don't remember which one it was.
Yes, it was ball bearings. So I was thinking of possibly implementing ball bearings on the bottom like rail of the blades. So if you go to the this year's design, so this one before, yeah, see how the blades have like a little tooth cut out right there?
Yep.
Yeah. So it was just a thought to try to minimize frictional forces, but I don't know, it's still in the very early phases. So do you have any feedback on that?
I would say ball bearings may or may not be the best idea. If you wanted to go down the route, I can, send you something that is more, I would guess needle roller bearings are probably more useful in that application. But, one thing that you're going to have to think about, depending on the size of the bearing cage is going to move half the distance of whatever you're moving it. So, your bearings aren't going to be stationary in there as well on that sliding surface. So they're going to be moving as well. So it'll be a sizing problem, but you might be able to figure out how to do it. But I think they'd be slightly better for the application that you're trying to do there. You're not rotating.
Okay. What was the name of them again?
Needle roller bearings.
Needle.
They're going to be round bearings as well, but what you would have to do is if you wanted to use them, you would buy some needle roller bearings, pull the rollers out of the bearing, and you guys would make your own roller cage for them so that they could roll flat. They're used in, machinery sometimes as well.
All right. Awesome. Thank you for the suggestion.
I'll also mention, if you are doing anything with your own bearing contacts and stuff, to make sure you're not like divoting your surface and stuff, they need to be hardened surface, especially for needle roller bearings, because they're very, very hard. So whatever is contacting them needs to be out of a hardened material. So you may need to figure out some sort of like high carbon steel that you can harden, or like a really hard material or whatever that you can machine separately and then like implant into your lighter aluminum structures.
All right. Sounds good.
That's a good point, Andrew. So next item on the list is the payload that you guys are doing. What is the purpose of the soil testing? What are you expecting to happen with this? Why was it chosen?
So the reason for choosing this specific payload was to determine soil health, if it's affected at all by high G forces when launching, say, into space. Because one of the ways to detect soil health is to see the variety and the amount of microorganisms that are present as they make the soil more rich and can give off nutrients. So we want to see if any of those are killed in our launch. And we think that will have decent effects, considering if we want to take soil into space at all, like I was mentioning. But yeah, what was your question about that?
Well, no, that's kind of what I was wondering. You guys really didn't lay out, why you were
Sure. And
Oh, I
putting
think
soil.
Yeah.
Ben joined after you
Oh, he
explained that
did.
slide in the beginning.
Yeah,
Just
sorry. I had
Okay.
another slide here in the beginning where I talked about it. We just want to make sure that the soil would be healthy, after our launch. But yeah.
Got
Yes,
it. Thanks.
I didn't know
Thanks for
that
explaining that.
you had missed that first part there.
So the static fins, you guys are talking about airfoiling them, which is, not a bad idea. I'm a little curious on what the idea of the aluminum bars is for.
Well, basically, one of my main concerns with this type of airfoil that we have, it's going to be very pointy on the end. So say the rocket lands on the ground and it like chips off or something. In order to minimize that, I wanted to add these metal bars just to add some extra support towards definitely the furthest points because they're going to be very thin in that edge.
So you're trying to reduce impact damage with them, I guess is what you're saying?
Yes, and then also it'll be the metal bars will go into the through the wall as well, just to also provide even more like support in that way too.
Okay, because if it was for support, the thing I was going to point out was if most metals that you're using are going to be not as strong and definitely less stiff than if you're using carbon fiber. So I don't quite know how useful they would be in that case. I could possibly see the protecting damage, but if they're still on the inside of the carbon fiber, if you damage some of the outside, it's probably not extremely flyable again. I mean, I don't know how competition would grade that, but just something to consider.
If I can just, because we're on the same topic, I hope you don't mind if I also add in a comment on the same issue.
Go ahead.
Benjamin, you're absolutely right. The carbon fiber structurally is going to be stronger than any metal bars inside it. So from a structural standpoint, they're not helping. In fact, they're hurting. They're adding weight without strength. But to prevent damage, and that's a totally appropriate use of these things because it is certainly tougher and more resistant to damage than the carbon fiber is. You don't want to mount it inside. If anything, you instead perhaps want to run those metal bars along the front and rear edge of your airfoil and build your airfoil around those metal bars. Let it be exposed. Let the metal take the shock of hitting the rock when the rocket finally comes down, or being a metal overlay on a carbon fiber structure so that it's more directly providing the shielding from your carbon fiber and taking the stress load off that you're looking for. It's not going to be able to do that as well inside the rock, inside the fin, as it would if it were applied around the outside of the fin instead.
Very good point. Yep. So something you could do, which I know is done in SAE sometimes, they do an aluminum structure. You could do an outer structure and then some type of foam or honeycomb or whatever on the interior, and then lay your carbon over that. But like Robert said, it's inside doesn't really help you very much.
Could I jump in for a moment too?
Yep.
Since we're in the concept stage, I feel a little bit more free to bring up radically alternative solutions possibly, but plenty of teams have come across the same problem and they've just accepted that their fancy fins that are of complicated geometries are just not going to survive. So they design it so that their fins are swappable, which also gives them a little bit of flexibility with, if the rocket is a little bit different, they can just plug in different fins. Now, there's a lot of considerations to come in there because, those are extremely critical flight components. So they need to be very well designed to be a very rigid mount and very stiff for, all sorts of fin flutter and other structural considerations. But that is another approach of just accepting that these things are weak. They are probably going to be a one flight item, and then you have a box of them in the trailer, and then when you recover, you swap them out for the judges and show that your rocket can be flown again.
Yeah.
I think I've seen some other teams actually do this approach. I was wondering on why, they had external connections for their fins, with fasteners through them, and I think this might actually be the reason why, so that they're swappable.
Yes.
That's definitely an option to consider. Sierra, you were going to talk?
Yeah, I was just going to mention that I think we kind of take this approach, like we've developed with the team, that we want to have backups of as much as possible at competition, but I would still rather that we try to develop something that is more structurally sound.
And we'll have to look into it with the test launches. I think that we can determine if these fins would survive, and then if they can't, then we'll have to look at a new fin can design.
Well, you mentioned it there as well, fin can.
Yeah, I've seen some rockets like that, and they look interesting with the modular sort of fin can.
Yes, and one of my questions following this was, depending on if you're going to do, rigidly mounted or replaceable, what is your flight profile looking like? Because you guys are talking about 2 stages at 30,000 feet, and you also mentioned supersonic fin geometries. So that starts to add a lot of complication there, depending on speed and acceleration of your chances of ripping a fin off.
Right, and that's why those fin connections would have to be solid. Sarah, based on the Open Rocket, is Open Rocket able to simulate those fins as airfoil there? Did you have it do that?
I believe it has the capability. Open Rocket has the capability to design to simulate them as airfoil fins. I just need to look into it more deeply to make it more specific and specialized to our particular shape.
Yeah, so I think we'll have to look into the analysis a bit more. I've actually been facing a similar issue with my rocket, in Open Rocket at least. My level 3 rocket has second stage fins that are not through the wall, so I need to do a similar thing to make sure they won't shear off in flight. So we'll definitely need to make sure to look into that. But yeah, Sarah, we can talk about the Open Rocket and make some changes to it and see how that goes.
What's your Mach number for this, for both flights? Maximum.
For the 10K flight, Sarah, correct me if I'm wrong, but I believe 0.6. And then for the supersonic flight, I believe the max was 1.4.
For the booster or the dart?
So,
or I'm sorry, for the second.
Overall,
dart, but the
overall,
second.
both of those numbers are correct.
Yeah, in 30K we would break Mach 1 twice because of the 2 stages.
Okay. All right, well, I'm all good on that. Talking about your ARM, AARM, how are you guys locking this in place once you rotate it in? How are you preventing it from, rotating the other way at some point during putting it on the rod or flight or whatever?
Andre, is there a locking mechanism that you have in place already?
Yeah, so this is a new system, and we didn't do a lot of thought about it.
So we'll have to add in a locking mechanism to this. Is there anything that you've seen done before that you might suggest for this system?
I don't quite know where it is. I mean, I like the idea that you guys have there of, I assume one part of this is a bulkhead that is in the rocket, and you're going to,
Yes.
Put it in and then twist it in, which is a good idea. It would depend on what kind of access you have from the other side. If you have any,
Sure. And the arm is
There should
located.
be pretty good access
Yeah,
here. I was under the impression we would just bolt it after, and this would act as a key feature similar to our payload.
Because you see we've got a parachute here, so there's a break right near it. So we have good access to it.
Okay. So, I mean, it could be as simple as, you know, putting a bolt through it, like Sierra said, something simple, or, you know, some type of pin method would
Yeah,
probably work.
I think with a system like this, keeping it simple would probably be the best thing.
And let me see, where's that at again? Is it on
The arm
the
is here.
soil? Arms right there. So it would be holding the avionics and air brakes, all that.
Yep.
Yes, and the arming system for
Okay.
the second stage motor.
So it's somewhat light system, you know, just be considerate of, you know, having these 4 pins and, you know, possibly ripping them out or ripping the slot out during some type of deployment event or landing. So
I think the
yeah.
pins would be an interesting thing to look into and try out, because that could potentially in the future be a way to get around very difficult integration spots.
I agree. It's a good idea. I'm just saying, you know, don't try and make that too thin, especially probably the slots. I would be more concerned about than the pins themselves.
All right.
If I could jump into something to think of also when you're coming to any sort of fasten joint is compression along like the fastening axis. If you think about how a bolted joint works, you know, it compresses things in, you know, a particular axis. With this particular design, there's no compression. Actually, it'll probably be somewhat loose, just to allow you to actually have a chance to put the thing, you know, on and off without needing a hammer. So it by itself will probably, you know, at least I would imagine it wouldn't be very sufficient for at least like a loaded joint of any kind. So that's just a thought I would have is with this as it is, it doesn't seem like maybe ideal for loading of most kinds.
All right. We will keep that in mind. Let me write that down here.
I don't know how well it would work, but one possible solution to that is to taper either probably the slot in some way so that you're actually building tension as you turn it in.
All right.
Is that similar to that sort of locking mechanism you mentioned in the past, Andrew? Kind of conical.
I think the one you're referring to, I apologize, it's been a long time since I thought about it.
Yeah.
So I don't know if we're thinking of the same thing. But I think the one I was referring to before what is a bit different. What Ben is basically talking about is basically making like a giant like half-turn thread, essentially, where there's a very, very light taper like angle to it. So you can basically keep turning it until it like, you know, you get compression along that taper like contact point. So you're getting like axial compression and then you're pinning into location. So Ben is basically, you know, saying the alternative is to make this a very, very big thread that doesn't go far.
That makes
like
sense.
a four helix thread, basically.
All right.
So probably the last thing for me for now.
Okay.
Something I noticed when you guys were doing, well, actually Andrew pointed out when we were going back and forth, was with your decision matrices, all different kinds. It seems like a lot of them, you know, you had decisions where you went, you know, you're going in some way, even though it's not favorable for how you have your decision matrix set up, which is not necessarily wrong, but you know, maybe there's some factor in there that is, you know, your cool factor, or, you know, you want to do it, or, you know, design points, you know, ingenuity type thing, that pushes it over. So that could, you know, maybe make that a little bit make more sense.
Sure, and I know we've seen alternate ways of doing decision matrices in the past. You know, some that have tens of factors that go into them. I think editing this to add in a couple other factors that would make some of our other decisions make sense would be a useful addition, and something that's pretty easy to do as well.
Yeah, and I would like to point out that the reason for these decision matrices aren't necessarily that they are meant to give us the answers, more that I wanted people to think about what was going into their decisions a bit more on a categorical level, and be able to argue if they did feel that, okay, well, this is really expensive compared to this other thing, or this may take up more size, but I think that the benefit outweighs that. And there is weight behind this you don't see in this calculation. It's not just an average. There are weights to this in our back end of it.
I would maybe propose in some of those cases it might be better behind the scenes decision making than presentation, if there's a, you know, like a factory of adjustments happening in the background that are not being presented. Just a thought on my side.
All right, we'll definitely have to look into the way that we do the decision matrices, and we'll see what makes the most sense for our decisions up and coming. Like Sierra said, they're not our determining factor for making the decision, but a tool to help people realize, you know, why they made that decision and be able to explain it to all of you.
But
yes.
Understand at the same time, just to play devil's advocate here, this is an engineering competition. It's not really rocketry. It's just rocketry is what we're using to have an engineering competition.
Right.
The way this is going to be judged, a lot of your score is going to be based on you explaining how you made the decision you made. And in a perfect world, an engineering report is a tool that a new engineer coming in after you can understand how you made your decisions and why you did, so that they can either make the same decisions because their logic is close enough to yours, or their circumstances are close enough that they can follow your logic to the same conclusion, or they know to vary off because of the nature of their circumstances. So in that case, I would say that the decision matrix is something that should absolutely continue to be featured in any of your presentations, and especially in the reports that you're going to submit to the competition, because why you decided what you did is at the heart of an engineering document.
All right. And I agree in that case that the decision matrix has to, you know, exactly match what we choose, unlike a couple of our decisions. So we'll make sure that it definitely reflects that, especially going into the reports for this year. All right. And you said that was all for now, right, Ben?
Yeah, I had a couple other things, but they're not necessarily pertaining to this.
All right. Well, next up we have Robert and Robert, but I don't know which one is first in the list because the names are the exact same. So if either of you have things to discuss, then now is the time.
Dad, you want to go first, or shall I?
Things, you know, one of my concerns is you're putting in deployable fins and then putting air brakes because you're going to fly too high anyway.
Mm-hmm.
You know, is there really that much advantage to the deployable fins, and that you couldn't just make fins that are, you know, put in place and solid and lose a little bit of altitude?
Right.
You know, and particularly, guys, I've built a lot of rockets over the last 15 years, from little Estes to 15-foot, 10-inch diameter rockets. The most critical thing in building every one of those that you spent the most time on was making sure the fins were equally spaced and square to the tube.
Mm-hmm.
You know, to me, the idea of a curved fin, I think of rifle barreling, and rifling in a barrel that you shoot a bullet through. I just think that rocket's going to spin like crazy, and if it's still spinning when you try to put a chute out, it may all end up wrapped together. I find those very scary, and I don't think there's anything in open rocket that is going to look at that kind of fin and tell you it's a problem.
All right. Yeah, I know that there are definitely limitations of that program. I know one of the fallbacks of that is doing just the standard opening fins, the ones that are centered on the rocket like we've done in the past. But you know, because they're wrapped around that 98 millimeter motor tube, there'd have to be 2 sets of them, which you know adds another level of complexity having them deploy at the same time. But as for doing deployable fins rather than static fins, it's you know the system that we did our podium session on this last year. It's a system that we've done for a few years now, and it's a very complex system that's nice for people to learn on. It's given us a lot of good insight. But Sierra, you know more about the origination of this than I do. If you could speak to that at all.
Well, everyone who is here has been around for a few iterations of the deployable fins. So I don't know how much I need to explain that to people who have been around longer than I have been around.
Sounds good. So yeah, so we'll definitely take a look at that, Robert, and we'll see if we can get away for Open Rocket to look at the roll, and if we can't, then we'll have to see if we can find some other way of estimating it before our launch.
I think the off center is a much bigger concern to me than the deployable.
All right.
You know, if they were deploying out like you did in the past, where they came out centered to the tube, that's pretty. You know, but this, that having fins the way like off center really scares me.
All right.
The other thing is some of the other stuff like the camera things to move the camera in and out. You know, you've got to assemble the rocket, and if you assemble them with something simple that puts them in place into the camera shroud, you don't need all that complexity.
Sure.
But that's just, you know. Other than that, I thought it was a good presentation. I thought it was, you know, well thought out, and I think it's a good starting point.
Great. Thank you.
Could I possibly make a quick comment? Sorry.
Sure.
Just to build on one more thing. Sorry. One more thing with the Open Rocket thing, just as clarification, there is 0% anyway you're doing anything off axis with the fins in Open Rocket. That's just way beyond the scope of what Open Rocket
and we've looked at other software as well. I don't think there's anything else that could do it. Yep,
No,
I see 3 heads shaking no.
That is a nasty problem, my friend.
All right. Well, that's a good indicator that the 2 sets of deployable fins might be a better option than we originally thought.
One question I have about the 2 sets of deployable fins is, Andrew, I remember you telling me at one point, and I don't know if I've imagined this, but I thought that you told me that there was some big problem that you guys had with big slots in the airframe. And my concern with these is that there would be big slots in the airframe in both stages, because one would have to be outside of the coupler tube, so it wouldn't be able to be concealed, and then we'd have to figure out something to keep the deployable fins inside before our second stage separate. Well, not second stage, but our dart separated.
Yeah, you didn't imagine that was recounting a nightmare from previous years.
Yes.
So yeah, but yeah, I mean that's essentially why in the past we've advised about adding internal structures to your deployable fin region, because of the amount of weakening, or for example, with WAFs, completely avoiding the problem by doing a completely internal structure for the stiffness of that joint. So yeah, I mean it's a huge problem, and certainly something to be considered greatly. Minimizing the amount of giant holes in your airframe is definitely a good goal.
Yes.
Right.
And the other thing to keep in mind is stacking them and avoiding stacking them. If you have to do 2 sets of slots, one over the other, rotate those slots off center to each other rather than putting them directly over, because directly on one on top of the other is going to weaken your airframe much more than if you were to have them offset.
All right. Yeah, we had not considered that. I believe that the original thought was similar to, how like split fins work, how they're just straight off of each other. But yeah, I can see how an off-center one would work if they're 2 sets.
And in a fixed fin arrangement, that can be fine, because you've got all the reinforcement and filleting at your fin root to the body in order to reinforce the weakness you've introduced into the airframe. With a deployable fin like this, you don't have that kind of opportunity to reinforce the airframe.
Sure. And a question, if we do this set of stacked fins, with the size of them, is it worth doing airfoil? just because of, yep, I see a no from Ben.
No, do not, please do not do that.
Yeah, I think that
That
they'd be
will-
so small that they
Jeez.
just get demolished on landing, and I don't think the benefit would be
And in
there.
fact, if you do the off-center, I would very strongly advocate that they are also flat slabs with rounded edges.
Okay.
That's the only airfoiling you do is just round over the front fore and aft edge, leave them as flat slabs. It's going to give you the most opportunity to avoid generating lift with them and spinning your rocket and turning it into a top.
Okay, great. Thank you.
If I could also, oh, sorry, go ahead, Ben. I see you in the webcam.
So the one thing I wanted to come back to too is, since we're talking, you guys are building a rocket for 2-stage 30,000 feet right now. A problem with WAFs is that as you start to go up in the Mach range, the rotation generated by the WAFs changed. Like once you got above, I think near 1, it flipped. So I don't know if it applies to this type of situation where you have a roll generated. That's something you guys will definitely have to look at, because like Robert said, there's a big problem with just generating a lot of roll in the first place. But if you are passing through up to Mach 1.4 or whatever, you could have something where, you have some funky aerodynamics going on that just rip them apart.
Right, and I think the main contributor to that roll factor is when they deploy, if they're off, that perfect 90 degrees from each other. At least it's that way for static fins. So I'm assuming, once they're deployed, then they interact with the airstream like static fins.
No.
But no?
The answer is
okay.
No.
So how's it different for these once they're out fully?
Because you are going to have an area of low pressure and high pressure on these fins because they are off axis. When you have static straight fins, generally, unless you have an angle of attack, your pressure distribution is even on each side. So with these being off axis, you're going to have a pressure distribution that's going to cause a roll. And one thing it wasn't, our finding with WAFs, but it was military finding that once you start going fast enough, say if it generates a counterclockwise roll below Mach 1, once you break the sound barrier, it will cause that to switch and it'll generate a roll in the other direction.
Yeah, I apologize. I didn't know you were talking about the off-center opening ones. I was talking about the stacked version. But I thought those would. I agree with you on the off-center, but on the stacked ones, if they're fully deployed, and provided it's toleranced enough that they are that 90 degrees, I think the impact to the roll should be minimal. All right, great.
I agree.
Yeah, based on the feedback so far, I'm shying away from the off-center opening, just because we don't have the ability to simulate it, and from what I hear, it's not the preferred method. So we'll definitely meet with Barnabas and we'll talk about our options for this.
Now, if you're doing a new member launch, a test launch sometime over at Muskegon, and you want to use it as a test bed vehicle to try out something new and innovative, hey, go for it, guys. Don't do it on your contest rocket because there's scores involved. But as a test bed, it's a very innovative approach, and I'd love to see what kind of results you got actually trying it in the field.
Yeah,
but
and I think
the contest is not the first time to try that one.
Right, and I think that could definitely be a thing that we do with Sierra's focus on getting L1s for new members and having more certified members. We're going to have other rockets available that we could add systems to. For example, my 5-inch rocket for L3 could be a candidate for applying the system to, just to see if it works, using it as a test rocket for the team. So I think that'd definitely be the preferred option to test the system.
It could even be, you don't need them to deploy necessarily. You're really interested in just, it being off axis. So you could, put some fins on solidly mounted on a rocket in a similar, angle and see what happens for relatively cheaply.
Yeah, I hadn't thought about that. That would be cheaper. I like this idea already. I'm having flashbacks to my budget slide already. But yeah, I think that'd be a good test.
Yeah, I will say if you do that, you'll definitely have to launch that on the faraway pads and not a very high power motor, because if you're starting fins this wacky configuration, I'm sure you're range safety officer probably won't appreciate the configuration of a big motor.
Yeah, I'll make sure to bring some bulletproof glass for us to stand behind.
Yeah. So, something to mention too of this stacked idea is that also doubles the number of mechanisms that could fail.
Right.
And they also, since they're in different geometric locations, they will also have different aerodynamic properties, because they're going to be from different positions, and they also have probably a noticeable effect on, like, with air brakes, if they're sufficiently far away, the downstream air will be relatively corrected. For this one, it's going to be pretty, like the upper fins will dirty up the airstream for the lower fins quite significantly, making the problem again hard.
And I just had a thought, actually. So this is based on a 3-fin setup. If instead of two sets of them, if it was just one set of maybe 4 or 6 fins, would that be a better option?
That something like that's a pretty smart way to get around it by having acting fins.
Because that would also, it would make no holes in the outside of the airframe, because it'd all be in the coupler, which would be really nice for the first stage.
The downside, though, is I don't think with your side loading approach right now, I don't know if you can really fit in.
Yeah, it wouldn't be like
fins
the
in a
off-center. It'd
cruciform.
be many of these smaller guys that open straight out, like previous rockets. So instead of 3, it'd be, either 4 or 6. Because I've seen...
Yes.
Yep, go ahead, Robert.
When you're talking about the center of pressure effect of your fins, you're looking at the profile of your rocket viewed from the side.
Sure.
Having 4 fins or 6 fins is going to greatly increase the profile of your fins as you look at them, which is going to give you a much larger effect on center of pressure. So if you can go with 4 or 6 fins, you will get all of the benefits of your double stack. So that is absolutely, if this is something you want to approach, that is absolutely going to give you the effect you're looking for.
All right, I think that's an interesting system, because I think all of our rockets in the past have had 3 fins. So I don't know how much testing has been done with more than 3. Ben or Andrew, you guys might know, but I think testing this with more fins would be interesting.
I think the first deployable fins had 4.
Oh yes, I think I do remember.
Sierra's
that.
right.
Yep.
So
all right,
6 might be a good idea. I mean, I just did some quick calculator math here. You guys only have, and this is not including motor tube, in between your 6-inch airframe and your 98 millimeter motor, not considering any motor tube, you have just barely over an inch of clearance in between the 2 tubes. So those are some pretty small fins. So depending on, I don't know what your open rocket looks like, but you might have a big challenge with stability, kind of like we did with our first deployable fins, where we ended up, I think that was when we poured a whole bunch of concrete in the nose, but
sure.
I don't remember.
Yeah, Sarah, do you mind if I show the open rocket? I have it, but I won't show it if you won't. If you don't want to.
Did you know that we have a 6-inch diameter this year, or were you going off of 5-inch?
I believe that was 6-inch. Yep,
okay,
that was 6 inches. You have 1 inch and 70 thousandths on each side, not including motor tube.
Yeah, I was just checking to make sure.
Yeah.
I will propose, since we're a little bit blue sky at the moment too, it may be also worthwhile taking a second look at WAFs, just because you can fit a lot of fin in a small area. Just I'll mention that as something to maybe do some thinking about.
All right, we'll definitely have to take a look.
That'll be if you have stability issues, something to consider.
Great. So I think Rob had just finished, so I think you're all set. If you have a list.
Of course I do.
I know.
Let's talk about your AARM coupler. Go to the diagram where you showed where it was at in the rocket stack.
Gotcha. Let me see if I can get it here.
You passed it.
Did I pass it? I was going to say, I keep passing it.
There you go.
Yep.
So you're mounting it in between your camera shrouds and your deployable fins, both of which are going to be generating vibration forces on your rocket airframe. So what that means is that those two plates are going to vibrate against each other horrifically during flight, especially if you're actually going to end up doing your 30,000 foot flight. That's an awful lot of time for it to vibrate, and it's going to shake pretty damn hard when you're getting above Mach 1.
All right.
Just allowing the thread length to hold the two pieces together is not going to be sufficient. You're going to need some sort of positive lock to keep that thing from vibrating apart on you. I like the idea as a way to quickly and easily join the two pieces together, but there's got to be some sort of mechanism, whether it's one side of the plate has a captured bolt mounted underneath and you screw in a bolt from the outside of the rocket after you've put it together, or something like that. You need some way to positively lock those two plates together once they're joined, so that they can't uncouple on you.
Yeah, it could be something as simple as a set screw that screws in from the outside and it's threaded between the two plates when they're in home position.
You lock them together, you drill out a hole
hold them together.
so each piece has a half a hole, you thread it, you tap it, and you put a set screw in it. Now it can't unscrew. Yep, absolutely.
Okay.
Let's see. Your air start. You asked for some comments on how you are going to secure your igniter.
Yes.
Plain old Gorilla Tape is your best friend.
Okay.
You literally you run the igniter down the side of the motor casing, around the bottom, up into the nozzle, and you coat the whole. You cover the wire completely with Gorilla Tape, the entire length.
All right.
And then you're set.
Great. Thank you.
Yep. Your sliding camera. Can you go to that real quick?
Yes, I believe that's up a bit. Sierra, correct me if I'm wrong.
You are wrong. It is in Payload.
Oh, no, it's in Payload. So sad.
It's okay.
Here
It's
we go.
He was
first
just saying
design
that. He
review.
didn't really want you to correct it.
How embarrassing. Oh,
I
my.
know.
Something to keep in mind. I appreciate that you guys are trying to be innovative, but there's a difference between innovation and complexity for the sake of complexity. You have a camera sliding horizontally out into a shroud that has a glass bottom. Instead, why not just mount the camera horizontally pointing out the side of the rocket and mount a 45-degree mirror inside your shroud body?
We had
So that the image is captured going down. Then you don't have to worry about whether or not your camera is going to slide back in when you're going to try and take the thing apart, and you don't have to beat it out with the rock again like you guys did a couple of years ago.
Yeah, we had thought about this. One of the concerns we had was, would the mirror vibrate so the picture wouldn't be very clear?
It's as solidly mounted to the rocket as the camera is.
So theoretically, they'd vibrate the same.
Exactly. It's,
Gotcha.
yeah, it's going to vibrate, but because that's the nature of what happens when you put a camera inside a rocket and fire it. But unless you're just going to hang the thing from some wires inside the shroud and let it flop around in there freely, which obviously you're not going to do,
Right.
it shouldn't introduce any additional vibrations on its own.
All right, Sierra?
I will also say, correct me if I'm wrong, but I think that had to be done because the piece to unscrew it was forgotten when going for recovery, I thought.
Nope.
Okay,
When we
so
crashed,
it didn't come out.
when we crashed it, damaged it, and it wouldn't go back in. So I beat it in with a rock during our 30 minutes of
real caveman kind of
Yeah.
solution.
Oh,
A
okay,
mirror
okay.
idea sounds a lot, removing complexity that was there for complexity's sake.
You know, and since you're 3D, it sounded like you guys were talking about 3D printing your shrouds. Pretty easy to just 3D print in a 45-degree slot in the sides of the shroud.
Right.
Then as you're assembling your rocket, you simply slide in your mirror and epoxy it into place. It's going to be solid. It's not going to be subject to any damage. And now you can just flat mount your camera inside your rocket body where it's nice and secure, and you don't need to worry about anything projecting through your airframe.
That sounds great. Thank you so much.
At one point, I think it was under the power management section, you guys talked about using some Samsung lithium-ion batteries. Just a reminder of the environment you're flying in, okay? I looked these batteries up online, and their operating range goes through 40 degrees Celsius. you are going to have 70 to 80 degrees Celsius on those batteries while they're sitting out there cooking in the desert sun waiting to fly. According to Samsung, that's their venting range. Having a lithium-ion battery start to vent inside your rocket is going to be a problem. So,
okay, yeah, I'll take a look at that.
Keep in mind the environment you're flying in and make sure, because you guys have so much electronics inside this thing, you just gotta, you always have to ask yourself, okay, this looks great, and we've got that one board that has a built-in video display unit because you're going to mount a monitor inside your rocket or something. How is that stuff going to operate under field conditions? And your field conditions, for those of you that have been out there before, Sierra, you were out there last year or in 19, weren't you? It's not pleasant out there.
Yeah.
It's god awful hot. That rocket, if it's going to sit for 20 minutes before you have to take it down because something went wrong or somebody else's rocket had a Cata and you've got to take everything down to clear the area, that rocket may be too hot to touch. Getting internal temperatures in that rocket to 75, 80 degrees Celsius is not just possible, it's likely. And you've got to keep that in mind as you're doing your design work.
All right, we will look into batteries with higher temperature ratings.
A couple other things to keep in mind. You're building a 14-foot rocket. Yeah, inevitably some of your switches and your activation ports are going to be up pretty high in the air. You just need to remember to take a ladder with you that'll get you up that high, because your rocket base is going to be a couple feet off the ground, so your nose is going to be 16 feet in the air instead of 14. Just project management kind of thing.
I will make a note.
I'm not trying to dish your presentation because it was a very well done presentation, although 140 slides takes a while to sit through.
Yep.
But you had maybe 10% of your of your content talking about things that were flight determinant. The contest, flight performance is 50% of your score. You maybe need to spend a little bit less time in the weeds on how you're going to build your electronic components and a little bit more time on how you're going to safely fly and recover your rocket.
All right.
And so just as you're going beyond the design stage, you need to spend more time on having a successful flight and maybe a little less time on trying to come up with an innovative way to slide the cameras out into the shrouds or something like that.
All right. We'll make sure for future presentations to include more stuff, specifically about the flight, as I agree with you. It is the most important part.
It's not presentation. It's how much time you spend working on this stuff.
Sure.
If you're going to spend 80% of your team's time working on something that only gets you 15% of your score, you need to rearrange what you're doing and how you're working on as a team.
Sure.
You know, you should be spending the most of your time on the thing that's going to get you the most bang for your buck. And in this contest, it's, did you have a successful flight?
All right.
Let's see, Ben. Unfortunately, you stole it. You're running a close second for the most annoying person in this call. So well done. You're learning. That's great.
I tried. Quick comment too, talking about the slides. Well, Robert brought that up. It's just something to think about. You know, maybe you guys don't need to spend the time, going real low level, like explaining, what parachutes are for and all these other things. Most of the people in these calls, do have some understanding of what's going on. So, I mean, you could leave it in the slides, but it may not, you might not spend time actually going through it.
All right.
And just one last thing to keep in mind. During these presentations, talking about your new member rocket, talking about your two-stage rocket, which isn't going to be part of the contest, that's totally appropriate, and I completely understand that. You want to make sure none of that slides into any of your reports that are going to be submitted to Ezra.
Okay.
Because they're only interested in your contest rocket, and anything you put in for other stuff is just going to confuse them.
All right. Thank you.
I'll shut up now.
All right. Well, I know Trent was here, but I think he had to run. So let's see. So we'll loop back around. Andrew, we are now ready for your glorious presentation.
I'm sorry to disappoint, but I think everything's been basically covered as far as like my major points.
Oh, no.
Yeah. I mean, everybody covered a lot. I feel like Ben took the biggest swath out of it. I feel like my brain and Ben's brains maybe a little bit too close to one another as far as pulling stuff out. But the 2 points that I'll mention, I guess, is for the Lapdog system. I believe that's a senior design project. Just from historical experience with student teams and senior design based aspects of them, they seem to have like a 2% success rate of like actually getting things for the rocket. So it's always fun to get a whole bunch of student team members together on a senior design project for something cool. But there's so many factors that you can't control now that it's a class subject that can be detrimental if you're relying on it or basing other things around it. So I would just put out some caution there as far as that goes.
One thing I would mention, Andrew, is that electricals, the way that I phrased it when they proposed this was that they would have to stick to our timeline and not their class's timeline, basically. That this is basically MASA project, and I mean, they'll probably be ahead on their project in their class because it is a 2-semester project, but they just have to make sure they're basically doing it like a MASA system that is also counting for credit. It's 3 MASA members who are very active on the team.
So the part that Andrew, might not have laid out there is, at least, Andrew and I were both mechanical, but you will find that often the requirements of your advisor / the class will clash with what you need to do for your rocket project itself. So just fair warning.
All right. And we've talked to the instructor a bit, to get approval for the project. But I imagine as it progresses, we'll see what other constraints they might try and put on us. So in that case, we'll definitely have to look at things. As it pertains to the flight of the rocket, even if this project falls through, there will be no change. As the air brake motor controller, now the GOAT, is going to, if this project does not happen, it's going to do the air brake calculations itself. So there is a backup plan in place in case senior design takes us so far off the rails. There will be nothing affected on the rocket. And that's really the best part about it being an electrical system, because I know previously it's been mechanical projects that have fallen through, which are more detrimental to the flight of the rocket. But yeah, I think we should be safe on that part, but we'll keep an eye out. Thanks for the warning.
Yeah, definitely. I mean, it's, I would just be very cautious. I mean, I would even I'm biased just because I've seen a few of these things try and fail in different teams various times. But I'd be biased to say that, this would probably be like the tier B, like, if it happens to be ready at the end of it, plug it in. I definitely would have like the other stuff developed as if this doesn't exist, is what I basically would suggest myself. I mean, that's all up to your guys' decision, but just from historical experience, that seems like that might be a wise approach.
All right. And I think the way the electrical systems are, done right now, I think that is going to be covered, because, programming for the air brakes, for the control loop and everything started for this rocket, because we're using the same system. And then any physical components can be offloaded onto other projects that can be put in its place.
Mm-hmm. Okay. Yep. Fair to mention it. So some other smaller points, just to loop back to the deployable fins. I know we spent a long time, so I won't go much farther, but 2 things to consider is when you are not exiting a cylinder from a normal direction and you're going off at some weird angle, the hole becomes larger for the same width of fin, as a note. And I know we were talking about, probably you guys shouldn't use an airfoil, but if you did, especially in here, that really blows up the width of the fin, which makes that problem even worse. So just some very minor notes. Okay. Let me see. Yeah, like I said, I think I jumped in most of the points that I had any major comments on. The only other thing I really have is on your new member payload.
Okay.
So it's a very minor suggestion. So this is more fiddly than anything. But I guess before the minor suggestion is just to clarify, this is not counting towards your payload to apogee mats.
That's correct. This is for the booster.
Yeah,
Okay,
we
cool.
can only submit one payload to competition, so this is a separate payload.
Okay, yeah, I was just checking because this wouldn't be considered a payload by competition just because it doesn't approach apogee.
Right.
But it sounds like you guys already had that covered. I just figured I'd cover the basis there.
Sure.
So the minor suggestion I had is that I think it's a nice idea to have just like a plug and play non-critical payload for new members. I think that's good. What I will say though is that this rocket's already very long. So any efforts you can do to decrease the length of the rocket will make airframe people much happier.
Yes.
Because when you don't have a rocket that's like 50 miles long, it's easier.
Right.
So I would maybe suggest trying to bump down the new member payload to like a 1U geometry or maybe like a half U geometry or something.
So originally I wanted it to be smaller, and then I started looking at the electrical components of it, and they need a certain amount of room from their boards to make sure it's not too hot and all that. So then I was like, I don't think I can go with as small of a payload as I hoped.
Yeah. And I think,
but it is sort of just taking the place of where the drogue mortar tube would have been, so that's about it with that.
Okay, yeah, it's just I think it would be good still to maybe think about it, because I definitely think you can. I mean, people fly things to space that are half U.
Yeah.
So obviously they can stick a lot into a small area.
Yeah, I know. Giving more space gives the new members more, flexibility with what they can do for their experiment. But I think it'll also be a fun challenge if it's, either a half U or a 1U, trying to make things as small as possible.
Yeah, because I think that's, to me at least, a very critical skill that is not as much of a focus with how ESRA is set up. Because ESRA is like, you need like an 8-pound payload. So most of the time it's like, how big of a chunk of steel can I get away with?
And that's what I was trying to sort of emulate with the maximum mass. And like I said, I wanted it to be a lot smaller, but then I just got worried because, again, I didn't want to give too little space for electrical and mechanical to both work in there. I don't know. I know that obviously electronics can get smaller, but I don't know at our budget if we can get them, and with our technology, if we can get them as small as like a space program could,
If it was cut down, because right now there is a board stack here with a flight computer, radio board, power board, experiment board, mock altimeter, and an RSC3. If this was cut down to be just an experiment with power just going into the board itself, and then it just storing data locally, that would really cut down on the size.
Yeah, but we were hoping to have multiple electrical members involved as well. And I know you guys have mentioned in the past that having multiple people on a board is difficult.
Yeah, that was my next point. Having this much space, at least for electrical, allows people to practice things that they're going to use in the main payload, because there are these discrete boards that perform this function. I don't know how much of this could be accomplished on one board given that size. But yeah, we definitely have to talk to electrical and see, if there's any way they could make it smaller or combine. Because I know electrical just got a new program that will make it easier for them to do designing and routing and things, collaboratively, instead of just by your lonesome. But we'll have to talk about that and see if we can shrink the payload at all.
But keeping your new members engaged by giving them the room to play a little bit.
Yeah.
At the cost of 4 inches of rocket length by going 2U instead of 1U. That seems a worthwhile trade to make.
I think it is invaluable. We'll have to see. It'll be dependent on how many new members we get as well. We're planning on pulling as many as we can. So the more people that we can keep engaged, the better.
Yep.
All right.
Oh, and I would like to add real briefly, to those of you that got certified last month, congratulations. I am so glad to see you guys flying rockets more and learning the skill sets involved in successfully putting a rocket in the air. I think it was fantastic, those of you that certified last month, and I'm looking forward to seeing you some of you out at the field this weekend to get 1 or 2 of you more certified.
Thank you.
Yeah, we found getting certified has helped us quite a bit. Even just thinking about the systems in our rocket.
Yep, exactly. You're
Yeah.
practicing your piano. That's great.
Yeah, we want to get everyone on Airframe certified for sure.
All right. Anything else for your other points that you had, Andrew?
No, like I said, I think most of it got covered with other folks. I think I'm all good here.
All right. Well, I'll open it up. Anyone have any last comments or anything? I know we've gone through the bulk of the questions, and it's now 9 o'clock. So I know some people want to go eat dinner or go to bed. So what do we have before we all head out?
I do have one thing I want to bring up real quickly. This is mostly in response. This is something I've been frantically Google searching in response to something else. Something that Robert brought up. I think I found some batteries or LiPo batteries have higher temperature ratings. Like they just go up to like 80 degrees Celsius, which is far above like what 9-volt batteries and other stuff that we've been using before does. I'll send them to you. They aren't any more expensive. I think at least that's what it's saying, but the actual data sheet for it doesn't seem very clear, but it's showing like what its capacity is at certain temperatures, and it's bringing those temperatures nearly up to 100 degrees Celsius.
So I guess a question on this for Robert would be solutions for other teams with this. If the highest commercially available that you can find, at least for LiPos, is 80 degrees. Have you seen other forms of passive or active cooling on the batteries?
I haven't been able to look at the team's payloads and things well enough to know what they've been doing, but it's not at all uncommon for people to have been actively cooling their rocket as it's getting ready to go out on the pad, and they may have a cooling blanket or a cooling jacket around the outside of the part of the rocket that is holding the power pack that only gets removed when the rocket is tilted to vertical and being ready, so that you buy yourself more time.
Okay, so maybe a sweater for our rocket, sort of like.
Exactly, or just making sure it's being kept in the shade, because it's the sun that's going to add it much more than the external temperature.
All right.
Yeah, but where are they going to find shade?
We'll have to bring our own.
Not much shade out there.
You're going to have to make it, no question.
Yeah,
all right.
We've also brought up in the past testing our batteries with heating devices, so Josh, if those batteries aren't that expensive, we can also
like
always
$10
buy some, test it, see how hot they can get.
Yeah,
if that sheet isn't very accurate.
I think
even if you're not worried about venting for those, you're certainly going to see some degradation in performance. So maybe, especially if they're inexpensive, you may have to go from a 2S solution up to 3S in order to maintain enough current once you get above 40 degrees C.
All right.
The consideration, Josh, for the batteries is even if they're in the same package size, the comparative capacity, because we don't need, even if we can find ones with more temperature rating, I could get more than as a result.
I posted in one of our chats. I mean, this thing, it's 4,800 milliamp hours, so the capacity is pretty good, and the current's like 35 amps.
All right. Well, we'll have to take a look. I think a combination of a battery with a higher ceiling for venting, as well as a rocket sweater or shade device, will give us everything we need, and we could take a cool picture with the rocket in a sweater. All right.
But Matt, if you want to look at it, I posted in one of our chats.
I saw.
Okay. Can I pull you guys off topic for a second here now?
Of course.
Go ahead.
So what's going on with 2021 rocket? Where are you guys at with that?
So manufacturing has started. More manufacturing needs to be done. The current launch date is set for September 25th out at Muskegon.
Yeah, main issue is that we need to get more people trained, and some of our members, like Barnabas, has been working towards his deployable fins being completed, but now the reason why he isn't here today, he is in Hungary. He is from there, so he's there right now, somewhere where he doesn't have Wi-Fi access. So that is something that I will have to pick up work on. Currently, I'm the only person I think who can use the CNC, but I need to ask Sean about that to check if we can get more people able to use that. But Yeah, we just need to train people, and some people don't feel as comfortable going in because they haven't manufactured in so long. Or at all.
One of the
So what's the realistic percentage of completing it by the 25th? Because we're talking 5 weeks from now.
that's correct. There will be a launch. I have no promises on September 25th.
Yes, we are aiming for September 25th, and if that is not possible, we will push it back.
But luckily, not going to 30K has given us more time, you know, to get in, to be able to push that back further. Because, you know, our 30K rocket originally was dependent on this test launch, so it needed to happen as soon as possible. But now we can push it back a little bit and not have as bad of effects as we would have if we were launching to 30K. So when there's a launch, we'll obviously.
If you do get delayed a little bit, I can always open up the field for you and activate the waiver some weekend later in the fall, or even into the winter if you want. If you guys want to try putting it up sometime.
Yeah, and that'd be great.
That'd be great.
And then we'll be sure, you know, to send out an email, COVID willing, that we're having a launch. And feel free to come on by and see us, hopefully not put it in the lake.
And I apologize, but my wife just waved a piece of cake at me, and you guys aren't as important as cake is. So,
all right, have a good one, Robert.
And we'll see you soon.
Thanks for your
have a good night.
Thanks for your comments, and I'll see you on Saturday.
I will say launching during the winter is particularly appealing at Muskegon with a frozen sewage lake
that
instead
would be
of
nice.
a liquid sewage lake.
I like that point. I never thought about that.
Yeah.
Why is not all the launches being done in the winter?
Yeah, Andrew, I don't know if you saw the Josh's L1 certification.
I didn't land in the lake, but I landed in that little stream that's pretty close to the lake. I guess I thought I had a angle far enough pointing away from it, but I guess a nice gust of wind told me otherwise.
Yeah, it was not clean water. But
I had to wash my rocket down and everything.
Yep.
It joined a long lineage of people who've lost parts of their rocket to that unfortunate body of water.
Yeah. Yep. I mean, thankfully, everything was recovered. I didn't have anything that really got damaged. So.
Just a little smelly.
Yeah, just a bit smelly, but
yeah, just a little human feces. That's all.
Oh yeah, just a bit.
Don't think about it.
He cleaned it.
All right. So if anyone else has to run, I know Andrew, Andrew Johnson. Sorry, you've stayed quite a while. Feel free to run. We're wrapping up.
Cool.
But yeah, any last questions or anything, or are we all set?